GNAN course. So for today's session, we have Dr. T. Srinivas sir from BARC. So he was the outstanding scientist at the BARC and he worked in the mineral processing divisions. So sir is going to give today's talk on exploitation of critical mineral resources, overview on characterization and pre-concentration techniques. So we welcome you, sir.
Thanks. Pointer. ఇది pointer. Front back. Front. Very good morning to all. My special acknowledgements to Dr. Professor Mohan and Professor Narasimha and his team, which includes young faculty like Vamshi and many others. So they have been telling that this GNAN course on critical minerals will be conducted since 2 months. Then I assured them that I will definitely give 1 or 2 lectures in which I feel I can do some justice. So in that connection, I am here today. So I really congratulate all of you for taking interest because I will say a few years back, minerals are not very much a field attracted by high-flying youngsters. But today, if you see, right from Trump to the local people also, they are talking about critical minerals. Okay, and that has become a talking point for the entire world. That is why I think it is the golden age, I will say, at least in this part of the century, this is going to be a golden age for those who are working in minerals. And all of us should be sensitive to one point, that this minerals is a multidisciplinary field. That means you can take geologists who can contribute significantly. You can also have a mining engineer. They are traditionally people in this mineral business. But besides that, many other faculties like computer science specialist, okay, and advanced, those who are doing some advanced course in artificial intelligence and data analysis and all those things, as well as those who are in chemistry. And of late, we are seeing civil engineering people also entering into this particular field. Metallurgy, anyway, it is there. Chemical engineering and chemistry, they are also there. So it is multidisciplinary in nature, including biologists. There is enough scope for so many disciplines to contribute towards this, for the simple reason that these minerals are present in the nature. And if you want to extract any of these things, especially the critical minerals, you have to have a system which doesn't disturb this nature in a very significant way, because they are present in very, what I will say, challenging metallurgical conditions. So if you want to really take them out from the Mother Earth or from any other waste, we have to have real novel and innovative methods so that our future generations doesn't get affected by our materialistic requirements. Okay. So with this holistic introduction, I will start my today's lecture. So I am not a professional, what I will say, like teaching faculty, but still I will try to do my justice. There may be some gaps here and there, some repetitions. I have seen in the curriculum schedule, Narasimha has given some talk on mineral processing. There may be some overlapping, but I structured my talk so that I am feeling comfortable and I am having that continuity. Okay, please forgive me if there is any, what I will say, overlapping of any topics. So this thing is exploitation of critical mineral resources. So please don't misunderstand with the word exploitation. This is the word which directly hits the mineral processing engineer. If I say utilization, if it's something like that, that is a different way. But exploration, exploitation are sisters. That is why I use the word exploitation, That means if a geologist explores a particular deposit, how to exploit it, how to give value addition for that. That is the idea behind choosing this particular title. Now, if you let us just see this, these things you may be knowing, but I will still continue. These metals have their origin from minerals. Okay. Now, what is a mineral? Mineral by definition is a naturally formed inorganic solid substance with a definite chemical composition and characteristic crystalline structure. This is a very ideal definition. Many times it deviates from that. And mixture or aggregates of minerals are called rocks. And then ores are nothing but assemblage of these minerals. Okay, that is, a rock is nothing but assemblage of these minerals. But this rock qualifies as an ore if something can be extracted economically from that. Okay, so again here there is two definitions: resource and reserve. Resource is something is present, no one knows whether it can be economically extracted on that day. A reserve is based on that particular day's economics requirement, and also it can be taken out in a very what I will say attractive manner, right? So that is a thing. Now, some definition of terminology is also important. We all know what is critical mineral, but this fellow interferes with strategic and atomic minerals also. Because I am from atomic minerals, I thought let me clarify. But at one point of time, all these things are together only, strategic minerals only. They are not called critical. They are all strategic only. So first of all, let us go to critical mineral, which you know very well by this time, I think, which is having lot of importance for the economic development of any society. At the same time, and also for the security of that particular, what is geological, this thing, boundaries. But it is having disruption in the supply chain. Because these natural resources, so-called critical minerals, they are present or they are concentrated in few locations only. And because of the everyday changing geopolitics, there may be disruption in the supply chains. So at that time, your main activity which is responsible for your country's security or for other civilian societal uses gets hampered. Therefore, comes the definition of these critical minerals, which are vulnerable for supply this thing, and which are having very significant importance in the economic development of any country as well as for its security causes. Now, what is a strategic mineral? This is very straightforward, only for defense applications, strategic mineral. But sometimes it need not be for defense also. For example, tin, for some time back, it was considered as a strategic metal. Why? Because it is used in the food storage, and food storage is also a very secure thing for some countries. No, so you have to store the food. So tin is a strategic metal. Okay, so that is a thing. When you come to atomic minerals, simply we can say those which are having nuclear applications. For example, uranium, straight away everyone can pick up. Thorium, everyone can pick up. Not only this, you also have to have some other which are used in the nuclear industry. For example, zirconium. Zircon-based alloys are used as a cladding in the fuel of nuclear reactors. Similarly, you require heavy water. Similarly, you require lithium-6 isotope. Lithium-6 isotope is used in fusion reactors and molten salt reactors. Okay, these are all development different what is utilities which are used in the nuclear total domain. So we have got even rare earths at one point of time were considered as atomic minerals because they do contain rare earth minerals, you know, monazite, xenotime, and bastnaesite. Monazite contains significant amount of uranium as well as thorium. Therefore, when you are trying to take out monazite, in many places there will be associated radioactivity. So that is why people prefer those deposits which are having bastnaesite and xenotime, because relatively they contain lesser amount of radioactivity. Okay. And similarly, if you take ilmenite, ilmenite also has got minor amount of radioactivity. That is why Indian ilmenite is not, we are not able to market it extensively outside because it contains some very trace quantities of uranium present in that. Okay. Similarly, you take niobium and tantalum. These two things are available as a mineral called coltan, columbite tantalite combined mineral. Now, this is a big conflict mineral. It is very much used in modern day materials like superalloys and all those things, which are extensively used in the defense industry. So there, these things are used. Similarly, you take molybdenum. Molybdenum and rhenium. Rhenium is a substitution in molybdenum. Rhenium mineral as such like cobalt will not be available. Very, very few minerals are there, economic minerals are there. Molybdenum is present in the nature in the form of mineral called molybdenite. This molybdenite is a sulfide mineral. So many uranium deposits contain molybdenum because uranium is actually these sulfide minerals are pathfinders for uranium. Therefore, even molybdenum and rhenium are also considered atomic minerals. And titanium. Titanium is extensively used in the nuclear reactors because of the heat exchanger. They have got good heat exchanging properties. Titanium also is very important. So present, this definition is going changed, and our government of India also, once upon a time they used the entire rare earths and many of these things, copper tailings containing uranium and all those things were enlisted as prescribed substances. Now slowly government is removing some of them, including lithium, beryl, etc., etc., and they have focused only on some set of minerals, and they have put a tag on that. Those which are containing 50 ppm or above uranium, they are only any other deposit, any rare earth deposit or any columbite tantalite deposit containing more than 50 ppm, 60 ppm of uranium, that only should be taken by atomic minerals. Otherwise, private people also can do the mining and whatever it is. So that type of, they are excluding certain minerals, set of minerals from atomic minerals and shifting it to the critical minerals. That is why the big list is slowly getting shortened, right? Now, what is the value chain of metal production? If you see how metals are produced, first is exploration geology. This exploration geology essentially consists of remote sensing using satellites and all. They will find out the favorable geological terrains, and then that is followed by geophysical surveys, that is which consists of magnetic survey, electrical resistance survey, so on and so forth. After that, it goes to geochemical survey. Geochemical survey is on-ground survey. Then comes the geological survey, followed by drilling. You actually drill it and see whether something is present or not. And then that is followed by reserve estimation. Second thing is mining geology. Once you find out a geological body containing certain minerals, you try to give a 3D modeling for that. How much is the ore body and how the mineral is getting mineralized in that particular setup, okay, geological setting. So that is how you do the geological modeling, which will be useful for a mining engineer, how to plan his mining. Now, when you come to the mining, we all know there are three basic types. There are many other types, three basic types. One is the open cast mining, you can see on the topmost. Second comes your underground mining, and third is in situ mining. Okay, so third is the safest of all, but it has got lot of conditions. Only under those conditions you can do in situ mining. For example, uranium you take. One of the largest producer of uranium is Kazakhstan, and they produce mainly by this in situ leaching. If you want to make this in situ leaching, in situ mining, I will say, in situ mining, then there are certain geological conditions. It should be present in sandstone type deposits. There it should be below the water table. Then that particular mineralization should be in the form of roll front type. That means when you inject any chemical into the system, that wherever mineralization is there, this thing should go in some inclined way. That is called roll front type. Then there will be drawing wells. Okay, that is why there are certain conditions to follow the in situ mining, but that is the safest of all. It will not disturb the nature in any big way, and everything will be done underneath. Very, very concentrated one comes to the surface. Other things are destructive in nature mostly. That is why mining is opposed, especially in countries like India, where population is very high and population density is also very high. It is not very easy to do this mining business. So a lot of public resistance will be there. Then comes mineral processing. So mineral processing is nothing but from the mined material, how do you take the valuables from that? It is a relative definition. What is valuable, what is waste? There is nothing like that. Simply because present day there is nothing like a waste. Everything can be utilized. Only thing is It depends upon our ingenuity to find a use for that. Everything can be used. Okay, once upon a time, again, it is history revisited. Coal fly ash is a waste. But during World War II, everyone looked into coal fly ash for uranium. Okay, I am referring uranium quite often because I am from that particular field. But today again, you see, coal fly ash is a repository for rare earths. Rare earths. Similarly, it is also people are looking titanium from that. People are now looking for lithium in that. So like that, if you go search and there may be many things which are available in that particular one, which are of use to the humankind in different ways. So mineral processing is essentially taking out the valuable things from the mined material, complete utilization of the mined material, that is mineral processing, separation of the minerals. Of course, sorry, then comes, oh, to go back. Yeah. And finally, you will make the product, alloy or whatever it is, which will be deployed in the product of your interest. That is how the metal and its value chain goes. Okay. I hope you are clear on this particular thing. Now, next comes our favorable topic, that is favorite topic, critical minerals. Very recently, India has given some list of 20, now 30. Initially, they told 30, but they have shortlisted to 24 in the later, what is the listing and all. But anyway, forget about that. First thing is, what is the characteristics of these critical minerals? Especially in many, I will say, whatever I am talking is with respect to India. Maybe it is true in many other countries also. They are lean in tenor. Lean in tenor means the grade is very less. Now, what is grade? I hope I am able to convey grade, recovery, and all. Did you come across in the previous classes anytime? Yeah. Okay. So the grade is nothing but the quality. Recovery is quantity. Simple, in simple words, that you will get to know in the metallurgical accounting classes. So they are lean in tenor, that will be very low grade materials, and then fine grained, that is their size is very, very fine. Again, fine is not an abstract word, there is a standard definition for that. So 100 microns, it is called fines. Less than 30 microns, it is called very fines. Less than 10 microns, it is called ultra fines. There is ASME definition for all these particle sizes. We have to go by that. So very fine means it is present less than 20-30 microns only, these minerals. Highly disseminated. Highly disseminated. Disseminated means they are not present in a single place, but they are getting in the rock, they are getting here, there, and all, like stars in the sky. Next is they are chemically refractory. This is why we have to apply our ingenuity. Chemically refractory, that is to take out the metal from that mineral, it requires aggressive processing conditions. Okay, that is why majority. I am not. I am talking in general. Some may be exceptions, may be there here and there, but they are chemically refractory. Then they are associated with multiple minerals. In a given ore, you take, for example, rare earths. Rare earths in a given ore, rare earths may be present in the form of bastnasite. It may be present in the form of parisite. It may be present in the form of monazite, or it may be present in the form of xenotite. So, what is the challenge in that? I can design my process conditions to suit one mineral. If they are present in multiple minerals, how am I going to shift these process conditions? That is a big challenge. Okay. And then they often occur as co-products and byproducts. As such, you cannot say the critical mineral ore. They are present, there will be a main mineral, and this will be byproducts or co-products. Okay. So, what do I mean by grade? If you see world over major deposits of rare earths, see how low it is. The grades are so low, excepting for very few in the here. Okay, many things, many places, many deposits, it is extremely low. And India, you cannot even put that point also. It is such a low. Our monazite in beach sands, very, very low, 0.01, 0.05 or something like that. In the beach sand as such, 0.1% max. Okay, so you cannot even display it in the chart also, Indian condition. This is what I mean by deposit versus grade. Now, coming to the what I will say, disseminated and present in extremely fine sizes. You can see here. See, this is a bastnasite mineral occurring in India, one of the Indian deposit, rare earth mineral. You see, they are all acicular in nature, needle type, and then the size is 2 to 10 microns. So both the shape as well as the size are not at all favorable for any pre-concentration or any processing. It's very, very challenging to get this thing out from that ore. Similarly, if you see this backscattered image, okay, you can see here, these things are present. You see, the total scale is 100 microns. You can see monazite, how fine it is, how it is dispersed. This is the meaning of finely disseminated. That means in the rock, they are present as spots only. So what is the challenge? Unless I break this entire thing, I will not be able to see the property of this particular mineral. Unless you realize the property of this mineral, you cannot separate it, either physically or chemically. Okay. Penetration of any chemical reagent into this particular rock is also not simple. It is very difficult to go inside. Okay. That is the challenge with the fine disseminations. Now comes the chemically refractory nature. If you see monazite or bastnasite or xenotime, you can see here monazite and xenotime, the lattice energies are very high, 30,000 kilojoules per mole. That is, the interatomic bonds are very strong. To break them, you require aggressive temperatures, aggressive chemicals, so many things. Relatively, bastnasite is less, 1800 kilojoules per mole. And parasite is also somewhere intermediate. Okay, these are the three rare earth minerals. Rare earth fluorocarbonates as well as rare earth phosphates. Just to give you an idea, what is the difficulty in the crystalline structure to break it? Because ultimately, when you want to recover them, you have to break the mineral, then only the metal will come out. Otherwise, so many other things are there. Mineral as such cannot be used in any applications. They are called, if a mineral is used as such, it is called an industrial mineral. Like phosphates, it is an industrial mineral. As such, you take apatite and put it in some soil conditions, it will release the phosphorus to the plant. But many of the minerals, you have to break the lattice and take out the metal of interest. So all these things play a role in the process design. Now you see here, for example, what I am saying, apatite. We were discussing about apatite only. Why phosphates are the resource of rare earths? Because you can see this is actually model analysis of one of the Indian this thing. This apatite contains, you can see here, cerium, which is a rare earth, lanthanum. Okay, these two are present in apatite. Why? Because if you look at the apatite chemical structure, it is containing calcium. The ionic radii of calcium, calcium plus 2, is almost equal to rare earth plus 3. Therefore, during the formation of that apatite crystal in the mother nature, there will be substitution of these things provided they are present in the vicinity, in the hydrothermal solutions. Okay. Similarly, uranium. Why uranium? In uranium minerals, rare earths are present because the ionic radii of uranium plus 4, 0.97 angstroms, is almost equal to rare earth plus 3. So in that solution, if rare earths are also present, they get into the lattice of uraninite, right? Similarly, they go into the lattice of apatite. That is the reason why these things are present as secondary, what is that called? Co-products or byproducts, right? That is the reason. Now, what is a scheme? How do you go for exploitation of a given ore to get the metal or mineral of our interest? So it goes like this. First, you have to characterize the ore, like pathology. When we go to any doctor, first thing he will do is blood test. Then only he will understand what is your physiology. Then he will go to the next step. Similarly, you have to understand what is that particular ore, how the mineralization has taken place. Then you can scheme out the methodology of recovering that particular mineral. So first is characterization. That characterization can be physical as well as chemical. That is destructive and non-destructive. What you see in situ is the mineralogical study. What you destruct and see is the elemental study. That is mostly chemical analysis. You can even do by instrumental methods like XRF, this thing, all those things. But the information you get through chemical analysis is more accurate than the other things. Okay. So first is physical or chemical mineralogical characterization. Based on the particular information, we will see it how we will select the process, how to go. Then comes the step. The mineralogical data also gives us what should be the size to which that particular ore has to be comminuted. Comminuted means size reduced so that the mineral of interest comes out from the host matrix. That is called comminution. This is very important because of the energy you spend in the processing, major part is taken by here only, and most inefficient operation. 1% of the energy you are using is useful for crushing and grinding. That is why it is most inefficient, but it is required. It is required for multi-purposes, to take out the mineral of interest, also for material movement. Boulders you cannot move. Boulders you cannot put in reactors. Therefore, you have to break them. You have to break them and put it in appropriate material transfer conveyor systems and all. So, comminution is the other step. Once you comminuate, you got two routes. Whether you can go for physical separation, taking into cognizance the physical properties or physical property differences between the minerals present, and then go for chemical processing, or there is no scope for physical processing, straight away go to the chemical processing. So this option we have to make a judgment, and all these things you can do by experiments only. Sitting on the table, sitting on the computers, these things cannot, because whatever said, and because unfortunately we don't have time, mineral processing is an art only more than a science to begin with in the initial days. Slowly, science has gone into that. But initially it was only an art. Some people, even today, you go to Africa, the so-called niobium, tantalum minerals are taken by artisanal mining only. People will see with their naked eye, the tribals, and pick out those things. They can distinguish different minerals. So artisanal mining. Physically only they will do, manually they will, manually they will do it. So, what we are telling, that is physical separation or chemical separation, or it can go to this route, physical separation followed by chemical, or directly go for chemical extraction. Why we always prefer to go by this route? For the simple reason, again, the economics wise, this route is always better. Even environmentally, physical followed by chemical is better. What is the meaning? When you do physical beneficiation or physical pre-concentration, the mass is concentrated, pre-concentrated. That means you remove all the waste, whatever you don't want, whatever you not require, and again take out only what is required for your desired product. So then what happens is, in the chemical processing, the load of chemicals, the heat required, water required, all these things will get reduced. Therefore, this has got always a preference over direct chemical processing. Direct chemical processing can be done only if your ore grade is very high. If the ore grade is not high, if it is a low grade ore, or if it is a refractory ore, always the preferred route is physical followed by chemical processing. Then most challenging in Indian context is tailings management. You are taking out hardly less than 1% of the material, but throwing the entire thing, bringing it to the surface and throwing it. So how do you holistically treat these tailings? Are you going to dispose it on the surface, or are you going to put back in the mines? So many options are there. So, but tailings management is extremely important. As a responsible, that is why people are nowadays using the word responsible mining. Responsible mining. You are not doing mining so that your stomach is filled. You are doing it so that for the betterment of the society and for our future generations. So tailings handling is a very important topic in mineral utilization or exploitation of mineral. That is why countries like India are facing a lot of challenges. Countries like China are not having that much difficulties because they never bothered about the environmental conditions. Today, China has occupied the entire rare earth industry because once upon a time, in that Bayana when they started, and they started producing rare earths and all, maybe about a decade back or a decade and a half back, they have spoiled 11 square kilometers area near Bayana. So much so their local population has not allowed. Same is the case with US. Once upon a time, US is one of the main producers of these rare earths in Molycorp. mountain pass. There also locals are opposing establishment of this particular rare earth industry because it is very, I mean, polluting in nature. You use lot of chemicals, lot of these things. So these things spoil the entire area. Therefore, rare earths, they look very attractive in the end game. But if you see the root, that is one of the most spoiling things. So that is why again countries like Australia and all are insisting on life cycle assessment. We have a lot of development in Australia on life cycle assessment. You don't see the end product. You also see the route through which it goes, the complete cycle and recycle. So life cycle assessment is very, very important. Okay. You have to design all your processing conditions so that this life cycle is environmentally very benign. That should be the bottom line of anything. Now, Now, coming to the thing, physical separation, what are the properties we are going to use in this? We use particle size for separation. We can use particle shape based on the differences. What I mean is the differences in the particle size, differences in the particle shape, optical properties. Some may be having one color, something else may have different color, something may be fluorescent, something may be phosphorescent, something may not emit any color. So for example, you take tungsten mineral like scheelite, it is fluorescent in nature. When you put UV light, you can see them glowing in a very, what is it called, that UV color will be there, phosphorescent. So based on the optical property. Similarly, radioactivity. Some of the minerals emit gamma radiations. So that we can track. Obviously, alpha, beta cannot be used for any separation, but gamma, it travels for a longer distance. So gamma can be used. Then specific gravity differences. The difference in the specific gravity between two minerals. Some may be light, quartz may be light, 2.65, 2.7. Mica may be light, but cassiterite is very heavy, 7.88 and all. Tungsten, very high, very heavy. Your niobium, tantalum minerals, very heavy. Uranium minerals, very heavy. All these things are quite heavy. So you can exploit the specific gravity differences. Then the magnetic susceptibilities, the magnetic properties of the minerals. Some may be magnetic, and in that magnetic also some may be ferromagnetic like magnetite and all. Some may be paramagnetic, may moderately down. There, some may be feebly paramagnetic, very low. Okay, like the gradation is there, but still you can use it, and that is only on relativity. What is the other fellow present? What is his property? Based on that, you will choose whether I can use magnetic susceptibility or not. Then the surface chemistry based differences. Two minerals may be alike, but their crystalline structure, disposal of the metals and their other structure on surface structures are different between two. Though they have the same metal ion, but their disposition of various other things in the crystal structure are different. Okay, for example, you take calcite and fluorite, CaF2 and CaCO3. Both have calcium. So in the olden days, people used to put reagents which have attraction towards calcium only. Then you cannot distinguish between calcite and fluoride. But if you see the disposition of calcium to fluorine, the interatomic distance, and calcium to carbonate in calcite, they may be different. Okay, so what happens is you have to design your molecule in such a way that it anchors the distance between these two anchoring points matches with the calcium-calcium disposal on calcite, which is definitely different from fluoride. Okay, so like the design of molecules. So surface chemistry based differences. That means you exploit the surface chemical only surface properties. That can be, and electrical conductivity. Obviously, some minerals are conducting, some are non-conducting. That also can be utilized for, these are the physical methods of separating the minerals. Then when it comes to the chemical extraction, oh, sorry. When it comes to the chemical extraction, we have got pyrometallurgy, hydrometallurgy, electrometallurgy, and biometallurgy. All these things directly or indirectly use the chemical conditions of that particular mineral for doing the necessary concentration. Okay, these are the basic unit operations which we use in exploitation. So in order to reach this stage, all the steps above are also required. Now let us go to the next one. This water you can Let us talk something about the characterization, because that is very important. So, characterization, resource characterization, when you apply to our field, that is mineral processing, it is called process mineralogy. It is called process mineralogy. That is, you are using the knowledge of geology and mineralogy, all those things, for your process linked. So you are slightly like in chemistry, there is called textile chemistry, there is called some other chemistry like that. That means the same basis is same, but you are orienting towards that particular domain only. So like that, the mineralogical and geological information you try to orient for developing the process is called process mineralogy. So if you see that, process mineralogy can be considered as a practical application of mineralogical knowledge to mineral exploration, predict and optimize how an ore can best be mined and processed. This is the definition of process mineralogy. It bridges mineral processing and traditional mineralogy. That is, this knowledge is used for mineral processing. Process mineralogy is applied in geometallurgy. This is a new field again coming up, geometallurgy. Ore characterization, process design and optimization driven by today's increasingly complex ore bodies and rising pressure to reduce operational cost. We have a lot of pressure. Ultimately, we are developing the process, designing the process in a backward way. If the consumer gets electricity at 4 rupees per unit, you have to make all the other back end, that is generation from a hydro plant or a thermal plant or a nuclear plant, from there onwards till it goes to the grid and goes to the household. Everything is dictated by the end price, not by the front price. They will not go in this way, they will go only from the back. So you have to optimize everything in that such a manner. Okay. Responsible environmental management also demands great understanding of the minerals, their textures, in order to reduce the risk. This is very, very important for tailings management also. This understanding of this process mineralogy. Now, what do we do in what is it called? Mineral characterization. So there are 4 components in it: mineral identification, mineral composition, ore composition, mineral texture, and liberation. These are the 4 components in mineralogical characterization. What do we find by mineral composition identification? This is what are the minerals present in that. That is phase identification based on specific gravity, hardness, color, refractive index, reflectivity, all those things. Then how do you actually find out a mineral in that? We use optical microscopy, provided the minerals are coarse. But if the minerals are present in very fine sizes, you have to go for instrumental methods of finding out the various phases. That is, we go by X-ray diffraction, we go by scanning electron microscopy or electron microscopy or quant scan. These are some of the developments so that what cannot be seen through a naked eye can be seen by the instruments using the electron wave properties of the electrons. Okay. Next comes mineral composition. What do we mean by mineral composition? Since formation of minerals is by natural process, they are formed in a natural way in the Mother Earth. There is no certainty that stoichiometry between elements is always followed. We know that a given mineral X will form in a stoichiometry ratio of X is to Y. But there is no guarantee due to the weathering, due to the other geological conditions which are happening under the ground, pressure, temperature, so on and so forth. This composition slowly gets drifted. So you have to know that, because that compositional information will change the property of the mineral as a whole. Something which is present as a non-magnetic may convert into magnetic, or something present as a ferromagnetic may drift to para, or it may drift further to weakly paramagnetic, depending upon what is its stoichiometry in the mineral of interest. Then for this simple example is how the transformation takes place from ilmenite to rutile. Ilmenite is iron titanium oxide. It is paramagnetic. But when you go to leucoxene, the iron part is leached out. So its magnetic property is slightly reduced. When you go to rutile, it is completely non-magnetic. It is titanium oxide. So how this happened? The slow removal of iron by Mother this weathering process or any geological process makes this stoichiometry altered. The same mineral gets transformed in different places. It is present in different forms. Even in India, if you go to the south part, mostly ilmenite is there. But you go to the western part, leucoxene is also there. Same way, ilmenite in our south is different in property, ilmenite present in the eastern part of the country, because the change in that composition of that particular metal. So this is a microstructural and micro-elemental information like isomorphic substitution, diadochic substitution. These things are what which change the mineral composition and change the mineral property. Okay, diadochic substitution means depends upon the charge to ionic radii. Suppose if the main mineral, the charge to ionic radii of that metal is equal to something else, some other element, and if it is present in the vicinity, this can as well substitute into that particular lattice. That is called the diadochic substitution. Okay, that is the thing. Then all these things you will get to know through electron probe microanalysis. Okay, you will know the actual spot analysis and understand what is the oxidation states, what are the chemical elements present, all this information. That is mineral composition. Next comes ore composition. What is ore composition? Ore is bulk. What are the various minerals present in that particular ore? So quantification of various minerals present in an ore is called ore composition, and modal analysis. Some 10 minerals are present, but what is the individual weight percent also? Some X is present to 20%, Y is present 5%, Z is present 39%. So that is called modal composition. So you know what are the various minerals present. You also know what is the weight fraction of each of these things present in that particular ore. That is ore composition. Next is mineral texture. How is the size, whether it is spherical or acicular or something non-spherical in nature, because all these things play a role in physical separation. Okay, it gives textural information, shows what is the size, then it also gives the shape. What is the shape of it, as I am telling. Then intergrowth, how two minerals have gone one into the other, how they are present. This is very important, because when you try to comminuate a mineral, whether it is going, suppose if two minerals are present like this, then it is very easy to break them. But if they are present enmeshed like this, whatever you do, something of X will go to Y, something of Y will go to X. So that type of intergrowth and relief, all these are all some thermodynamics. It is driven by thermodynamics. Now, when something is formed, we always go to the lowest the state of free energy. So all these things happen in geological formations because of these things. Next comes liberation, extremely important. Liberation is the size to which a given ore to be reduced so that the minerals are liberated to a great extent. Again, this is a link to the unit operations which you are using. Suppose, suppose you are doing gravity separation using conventional methods. It is, even if it is liberated at 50-60 microns, I am happy with that. But if I am using some magnetic separation, okay, then 50-60% liberation is not sufficient. I want much more liberation. Otherwise, the property may get masked. The original property may get masked. So it is related to the unit operation which you are using. If it is a chemical operation, even 10% liberation is also okay, because I only want a way so that the leachant or the chemical which we are using penetrates into the near the surface of that particular mineral. So 10% liberation is also okay, provided it is highly porous, right? So that is the thing. Liberation is achieved by breaking the rock in the comminution process. You are breaking it by different methods. Liberation is essentially release of valuable minerals from the gangue. What do you mean by gangue? Gangue means unwanted. Okay. Next step. So this is the information we are going to get in the mineralogical character. Let us understand it furthermore. Mineral identification. I have taken an example. What do I mean by that? By doing the X-ray diffraction analysis or by ore microscopy, 4 different places you see, this is what? Different minerals present, quartz, chlorite, magnetite, all these things are present. And then this shows what is the weight of individual things present. Quartz is 68, this fellow is 22, like this. But when you go to some other ore, This is 36 and 52. So this information is very important because this entire ore body is hardly in 15 kilometers length. You can see in 15 kilometers length, the mineral composition is varying. The ore composition is varying. Here it is 68. When I go here, it is 36. Somewhere else it is 48. And in the end, it is again 67. So whatever separation method I am following may not work for entire thing in the same way. It differs from place to place. That is why the origin of geometallurgy. That is the origin of geometallurgy. You do sampling at different places in the ore body, try to find out its response to the processing. That is geology information blended with metallurgical information. Then you design your plant. Okay, that is what geometallurgy is. See, this is a typical example. In a total distance of 15 kilometers, how much these are different places in India, in East India, okay, uranium places, how these things are getting changed. Now, let us see another one. I am talking about texture. I was telling you, no, here you see very nicely it is emerged, very easy to break and release the red one from the green. But when you go further and further, it will be extremely, they are present in a different way. Here it is like a lump, whereas here it is lot of reliefs are there in between. So when I try to break it, what happens? So many fine particles will generate. Though volume wise it looks same, but when you do the comminution, this will give more, the mineral of interest will be in finer sizes compared to this or this. So the textural information is important. Next is, you see mineral composition. I told you ilmenite. You can see even wolframite. Wolframite is tungsten mineral, prominent tungsten mineral. It is iron, manganese, tungsten. So what happened? These are the what I will say, generational products of wolframite. When the manganese content is reduced, it converts into ferberite. Its magnetic property is different from wolframite. When this iron goes further, it is hubnerite. So each country, for example, you take in India, we have got tungsten deposits in some places, like Begana in Rajasthan and all. Okay, we have predominantly wolframite deposits. But when you go to Russia, mostly it is ferberite. You go to some other country, it is hubnerite. Understood? Again, one very subtle point in this is the tungsten content, which is the main element here of interest, differs from here to here to here. You can see that there is only manganese and tungsten are present. So if you take the molecular weight of that, the tungsten assay will be high. When you take this, it will be different. When you go here, it will be different. So it is not just I have a rare earth deposit. In what form it is, what mineralic form it is. If it is present in monazite, so monazite contains some percentage of rare earth. But when you go to allanite or some other mineral, the content of rare earth in that is again low. All are rare earth minerals only, but only few qualify as economic minerals. That is, minerals in which the element of interest is slightly on the higher side. So this information also we get through that particular thing. Next comes liberation. So you see here, see this particular thing. Suppose this is synchesite, which is nothing but a cerium mineral, cerium fluorocarbonate. This is present in green portion. So this, in order to release this green portion, it undergoes, we have to do we have to make a clear understanding of what are the associated things, and to what size it should be size reduced so that the green fellow comes out exclusively. And this green person is there in different sizes, you see here. So many sizes. Again, the choice of liberation depends on, as I was telling, the unit operation which you are using. So both the things you have to keep it in mind and then design your comminution circuit. So something, if it is like this, 25% liberated, that is okay for me for some chemical processing. But for using physical processing, 100% liberation is required. That is how it goes from here to here. So how do we find out this liberation? There are two methods, conventional optical microscopy based method, and present day we are using what is called instrumental based, that is called mineral liberation analyzer. This mineral liberation analyzer not only uses the instruments, but it has got enormous database so that whatever the instrument sees, the microscope sees, electron microscope, it will immediately analyze it and then give you lot of information, whatever we are observing through optical microscope, like size, shape, liberation, intergrowth, all these things it will give in an automatic way. It is called automated mineralogy. Okay. Now, first let me talk about how to do manually, because whatever, even though you are using an instrument, you should know the philosophy. If you don't understand the philosophy, you cannot understand the numbers. Modern day equipment gives only the numbers. It will not give the philosophy. Okay, that is the difference between present day mineral processing engineers and olden days. Olden days people, I will say even my generation's previous also, looking at the things, they used to sense what is happening. But today everyone sits before the computer and tries to, you may not understand everything unless you go to the table, working bench. You will not know. You say, during, for example, you do any froth flotation. I'm just jumping froth flotation. See how that froth structure is coming out. All that information you will have understanding only if you see the phenomena there. If you don't see the phenomena and see in the system only, you will not be able to appreciate it much. Okay, so it is a practical subject having a lot of shop floor importance, mineral processing. So how do they find out liberation? Olden days, I will say. First, they will take the ore sample. Then that ore sample will be divided into different density fractions using heavy media separation. So the liquids which are used for separate, they are called density liquids. One is bromoform, another one is methyl nitrate. Then by blending some other liquid, we can change the specific gravity of the liquid. This bromoform has got a specific gravity of 2.7 or something like that, 2.65 or something. So if you put any ore into that bromoform, it will be divided into two fractions, bromoform lights and bromoform heavies. Bromoform lights are those which are lighter than that particular liquid. So mostly quartz. That is, all other minerals get concentrated into the heaviest fraction. Now the whatever you get in that bromoform heavies, you want to further divide. So you go to a liquid which is of higher density further. That is called methylene iodate. That methylene iodate is specific gravity is about 3.25 or somewhere around that one. I don't exactly remember. So if you put that bromoform heavies into methylene iodate, then again they will be float and sink. What will sink there is heavier. What will float there is micaceous minerals, because they have specific gravity about 2.8 to 2.8, depends upon what type of mica it is. So it will go into the lighter fraction. You can separate mica further. So you are present with the most heavy minerals. That will be useful for your optical microscope, because if something is present at 0.5% and you see the entire thing under microscope, is it easy to identify that 0.5 among that one, 99.5? Extremely difficult. So what you have to do? You have to do pre-concentration. How do you do this pre-concentration? By this method. This is one method based on density. People even do further to this magnetic separation also. From that 0.5, how much is magnetite? Remove that extremely magnetic material and separate out the other things and use those things for observing under a optical microscope. So based on that, the liberation used to, which physically they used to see. They used to go from one edge, they will place that particular thing using thin sections and polysections, okay, and then do the grain counting using reflected and transparent microscope. This transparent microscopy is used for lighter mineral, which will allow the light to pass through it. Reflected microscopy only for the opaque minerals. Okay, based on that, physically they used to see and make a noting on the side. Okay, and then they used to give an idea about what is the liberation size. Now, present day, especially the critical minerals, or you take any other thing, the ore grades have depleted. Ore grades have depleted. Very difficult to do by this conventional microscopic methodology. That is why maybe about 3 decades back, again thanks to our Australian friends, they are the first people to design this mineral liberation analyzer in JKMRC, Julius Crush Mineral Research Center. So thereafter, so many developments have taken place, and that is the first place where there what they use is scanning electron microscope. The same thing will be watched under this electron microscope, scanning electron microscope, which will be fitted with some backscattered the X-ray EDX, as well as those which can capture the backscattered electrons, all those things. Using all that information, you can get a clear picture. And these are all artificial colors only to distinguish one particle from the other. So based on all this information, it will immediately tell what is present in this. Besides the electron microscopy, whatever information it is getting, it has got a lot of database. That software will be useful in understanding the information captured using this electron microscope, as well as that backscattered electron images and all those things. It will give all the information related to that. And also another beauty is it can go up to 3 micron size. 3 micron size. Up to that, it will give you what is present in that particular ore body. Okay, so you are presented with a lot of information, useful information, very nicely dished out for the process engineer to use that data. Now, after you get all these, what is the use of each of these things in your process? Mineral identification and texture details are useful in process selection. I hope you are understanding this. Quantifications of minerals is useful for designing the capacity of the equipment. They are useful in if you do a chemical reaction, what is the stoichiometry of the reagents. If something is present 2%, how much sulfuric acid has to be added. If something is present at 1%, how much I have to add. That is defining the stoichiometry. Then the heat balance. Some minerals, while they are reacting with the associated reagent system, they will give out the heat. That heat is proportional to the quantity of that mineral present. If it is present as 0.5, the heat generated may not be significant. But if it is present at 5-6%, the exothermic heat, for example, pyrite, iron sulfide mineral, if it is present in the system, if you are using alkaline conditions, the pyrite reacts with the sodium carbonate or sodium bicarbonate, and it generates a lot of exothermic heat. So that heat is proportional to the quantity of the mineral present, right? So heat balance it is. And then solution chemistry. This is extremely important. Once you put a mineral into a system, leaching system or anything like that, it will dissolve. Once it dissolves, what is the composition, chemical composition of the leach liquor? Based on that, your next step will follow. How much waste I have to remove, how much required reagent I have to put, all these things. Then metallurgical accounting. Most important is that to calculate recovery, whether that plant is operating efficiently or not, I will get to know through metallurgical accounting. Now, when you go to the liberation analysis, how does it benefit you? It benefits you by designing the comminution requirements. It benefits you by the type of equipment to be used. Because when you take physical properties, some equipment may be successful in separation or efficient in separation if the particle size is 20 micron, 30 microns. If it is present as 1 micron, 2 micron, if you are using a gravity separator, then the conventional equipment may not be useful. You may have to use centrifugal separators, which will amplify the gravitational force, right? So that is again dependent upon the liberation analysis. So what is the size to which the mineral is present? Then, of course, type of equipment to be used. What is the type of fine particle separator or a coarse particle separator or a magnetic separator or a high gradient magnetic separator or conventional flotation reagent or a chelating type of flotation reagent, or you have to use a dispersant, not required. All these things are informed from the liberation. Then tailings characterization. This also we have to do. That will be helpful in process performance evaluation and tailings pond design. Tailings pond design, these two. So that way, the characterization of the ore will be helpful in multiple ways. So this is the bedrock of designing any flow sheet, right? I hope I am able to communicate. Okay, right. So can I just for a break for me also? I am not a professional teacher. That's why I want break often. Can I know what are the disciplines from which you people have come? How many are geologists? Raise the hand. Very good. One geologist. How many are chemical or chemistry? Oh, good amount. 1, 2, 3, 4, 5, 6, 7. Right. And how many are metallurgical engineers? No. Mining? I can see from his face, mining engineers. Then any other branch, biology or anything like that? Civil biology, anything like that? No. Okay. Right. I am a chemist only, but I spent all my service period in this thing, mineral processing. So that is how I am getting transferred all these things. Okay, good. But my basic qualification is chemistry only. MSc chemistry, PhD also chemistry. Right. So let us go to the process part next. Again, I will take some. మీకు అది చెప్పండి బ్రేక్ ఎప్పుడంటే అప్పుడు ఎలాగైనా తర్వాత కూడా సారీ ఐఎమ్ టాకింగ్ తెలుగు తర్వాత కూడా ఎట్లయినా ఒక కొద్దిగా మంచినీళ్ళు తాగి ఇంకొక 15 నిమిషాలు చెప్తాను అప్పుడు గంట అవుతుంది కదా అప్పుడు మళ్ళీ చేద్దాం. Now, having got the characterization of that particular ore which we will go for the process. Again, I'm just recapitulating. After you do the characterization, we have to choose whether we have to go for, what is the comminution requirement of that particular ore body, ore. Okay. Now, just is a repeat slide. Yeah. Just is a nutshell slide only. What are the challenges in processing complex ore bodies? That means those which are finely disseminated and all. You need to mine more material if it is a lean tenor ore. Because to get 1 ton of any material, you may have to mine some millions of, maybe lakhs of tons and all. Finer grinding for adequate liberation. You have to grind more and more. Need for amplification of the separating forces. If you are using physical separation, instead of 1G, you have to use 10G. Instead of what is it called, a normal magnetic separator, you have to use a high intensity. If it is not captured under high intensity, may have to go for high gradient also, like that. That gradation takes place. Increase the consumption of mining chemicals. What does it mean? If my particle size is less, its surface activity, chemical activity is more. So what will happen is the consumption of the reagents also will increase. The surface area is more. Therefore, the flotation reagent you need to add also will be more compared to a coarser size particle. So mining chemicals requirement will be more. Next, larger footprint for a tailings disposal. Once you have finer particles, the volume occupied, the footprint will be more. So the tailings pond should be very, very enormous. And then complex rheology. In material movement, once the viscosity increases, the pumping requirement, all that material movement systems, they will be becoming more and more complex. So the rheology itself changed. Rheology affects not only in the material movement, but also in your process, separation process also. Okay, a more viscous system is difficult to, from that to get the selectivity than a simple system. That is why if you take in your laboratory studies, you do everything at 1% solids, 2% solids, 3% solids. Then you will get extremely good results, idealistic results. But when you transform to an industry, the results will be 50% of what you get in lab. Because there you will do not less than 40-50% solids concentration. So once that 50% solids concentration is attained, the rheology itself is different. When the rheology differs, the mass transfer process differs. Therefore, everything changes. You have to do sort of scale up. Okay, so your finer particles will change the entire rheology. And finer particles also enhance the dissolution. Because the chemical activity is more and more goes from solid phase to the liquid phase. Once it goes into the liquid phase, when you are disposing, you have to neutralize it and reprecipitate it and remove them. Otherwise, there is some limitation on that. For example, you take manganese. Manganese discharge limits are very stringent. You cannot have more than certain level of disposal of the manganese. Okay, so you have to precipitate it by neutralization and then bring it in the clarifiers put it in a secluded place. So when the particle size becomes finer and finer, this is another complexity. Another one is increased water requirements. The water requirements also increase because solid liquid separation will not be effective. Suppose you have a coarse particle, you do the process after gravity, you allow it to settle down very easily, everything settles, and you can clarify the water and reuse it. But if you have something like a very fine particles, longer time is required, wider diameter thickeners are required, okay, and more area. Everything may not be clarified water may not be coming completely what is a solids free. It may have some amount of some ultrafine particles or whatever it is, which may not be suitable for recirculating. So therefore what happens is the water, you have to always think in an industry point of view. When you are treating 1 ton of ore, it requires 1 meter cube. Thumb rule is 1 ton requires 1 meter cube. You can imagine enormous amount of water consumption in this mineral process. So we have to be conscious of this particle size. Ultimately, it goes back good understanding. And another important thing is in mineral processing, it is multidisciplinary in nature, I told. We should be able to transfer our understanding to a geologist as well as to the chemical engineer. The lab fellow should transfer, the mineral processing engineer has to put his hands on the both sides. This side to the geologist, to the other side to a chemical engineer who does the scale up. Okay, then only there will be seamless transfer of understanding and the better thing will evolve. We should always be conscious. We should not work in silos. That is a problem in many places. Similarly, what I will say is the mineral processing person or say geologist, he should give the complete understanding of that to a computational engineer also. Then only he will understand. For example, you have this, someone is developing, say, mineral liberation analyzer. In India, they are developing. So that fellow who develops is different. He is from a different field. He may be a physics fellow. He may be some other metallurgist who has no touch with the minerals. He knows only metals. He doesn't know this. So you have to make him understand all these things. Then only you will be able to develop a appropriate system. Okay. So it is interdisciplinary in nature. All of us have to work hand in hand so that the better thing comes out. So I gave the results of all these fine particles: low particle momentum, high surface area, high surface energy. These are detrimental for any separation process, right? This is the conclusion of that. Now let us go to the communication. So, okay, we'll break from here onwards. We'll break. So just to recap, we have covered the topic of characterization of any resource. I will say like that instead of saying ore or anything. Characterization of a resource and what are the attributes we should be tracking so that we get complete information on the pathology of that particular resource. And in that process, we also have seen what are the challenges when you go to the finer size particles, because many of these critical minerals, I forgot to tell, besides refractory, besides lean in tenor, besides what is a multiple mineral phases, and then occurring mostly as a co-product and byproduct, they are also very friable. Friable means when you try to apply any pressure, they get into powdery form very quickly. So once they get into powdery form, separation is always difficult for various reasons. I have given the reasons here. Okay. So now let us go into the processing part. So the very first step in the processing is, as I was telling, comminution. This comminution is essentially having two deliverables. One is liberation of a particular mineral from the host matrix, and second thing is giving such a granulometry or such particle spectrum so that the material movement is easier. At different stages, at mining stage, the comminution circuits are present underground, also they are present above the surface. Okay, underground because once you blast it, big boulders will be coming out. So you have to do some stage of crushing there so that it can be hauled to the surface. And once it comes to the surface, your process will dictate what is the size to which it has to be reduced. So in case 1, it is a material movement. In case 2, it is a process determined. right? So this particular figure will give you how things are present in a given rock. Okay, different minerals are present, a variety of minerals are present, and to capture the mineral of interest from this particular rock is really a difficult task, as you see it. Now, what we do? See, the first step, as I was telling, crushing, that is followed by grinding. Crushing is the primary step. So, this crushing is a very, very energy intensive operation. Almost 30 to 40% of the energy you are spending in a total process goes towards this particular step. Okay. And another thing is, it is most inefficient stage. Of 100 units you spend, energy you give here for crushing or grinding, only 1 or 2% will be effectively utilized. Rest all will go as some other mechanical wear and tear, so on and so forth. So we have to really be careful in designing our comminution circuits. This is a costly process, energy intensive process. So all these things, inefficient process also. So it essentially the particle breakage takes place by three different mechanisms. One is the compressive, another one is impact, third one is the attrition. So depending upon which mechanism is dominant, the granulometry of the particles that generates that unit operation discharges will be dependent, right? So let us see. Now the energy during this comminution process will be, as I was telling, will be distributed for breakage of the material, for wear and tear, for plastic deformation. It may not generate any particle, but it will give plastic deformation of the material, or vibration and noise. This is how the energy gets distributed. Now when you look at it, energy consumption in crushing is about 2 to 5 kilowatt hours per ton. While in grinding means further size reduction. In the case of crushing is about the reduction ratio, it is called. Reduction ratio means feed size to the discharge side. It is about 3 to 5 max. But when you go to the grinding, it may be much more. It is not actually defined because it will be extremely more than 100, more than 200, or it may be more than 1000 also, depending upon the mineral property. Therefore, in ball and rod mills, which are conventionally used for grinding purpose, the consumption of energy is 10 to kilowatt hours per ton of that particular thing. Now, here, this is again an infogram of how energy is spent in a given process circuit at different stages in crushing, grinding, processing, tailings management, process water handling, general plant, and total. So you see here, major thing is in processing, that is immediately followed by crushing and grinding. You can see here the bar graph. Okay, so that is how the energy gets distributed in a comminution circuit. Now, if you see, the challenge in mineral comminution or size reduction is generation of fine particle sizes. How do you generate these fine particles, whatever is present in very fine sizes, from the host matrix? That is a big challenge. The target is, because conventional machines have got, conventional crushing and grinding machines have got their own limitations. So the challenge is new equipment which can give these finer size particles with less energy, and design of hybrid comminution circuits. How do you design it? How do you connect one to the other? Okay, process circuit. And then also use chemicals called grinding aids. These grinding aids helps in dispersion of the particles within a system, that slurry, so that the individual particles will have the effect of grinding. Otherwise, the cushioning of particles as an agglomerate will dissipate whatever energy you are giving in a non-fruitful way. So grinding aids. These are the three areas where the focus is on when you are generating the finer particle sizes. So let us see. You can see here, initially it was jaw crusher. This is present in the underground mines as well as above the surface. Then comes the primary gyratory crusher, then cone crushers. These are all primary and secondary crushers. That means it will bring the particles from very big sizes up to about 16 inches or even 11 inches, like that, up to that. Okay. Now subsequent, here the prominent mechanism is impact. In all these crushing machines conventionally used, it is the impact force. But there is some limitation for that in release of in size reduction of the materials. Then comes the invention called high pressure grinding rolls. Here what we do is, you have two rolls which are rotating in counterclockwise direction, which are having these hydraulic cylinders. It actually slowly compresses the material. What is the benefit of compressing the material in a slow manner? Here it happens in a very random way. The residence time the particle spends between the two crushing surfaces is very minimal. Here it goes in a very calculated and what I will say calibrated way. So what happens is once you crush it, the residual forces tries to be within the system itself. So in the subsequent grinding stage, that can be utilized. The energy, the breakage it initiated can be used in the subsequent stages. This is a great invention in the crushing and grinding crushing stages. Now comes the conventional. This is the ball mills. In the ball mills, the reduction of size to finer sizes happens by two mechanisms, that is cascading and cataracting. So once the material is moving like this, okay, it is a cascading effect. When it goes to the top, okay, the ball mill rotational speed is defined what is called critical speed. Critical speed means the entire charge is there now inside. That should not go as a centrifuge. If the speed is more of the rotating bowl, the balls will be sticking to the surface only. It will not go to the top and impact, fall down, so that breakage takes place. So you have what is defined as critical speed. Critical speed is defined in such a way that it goes at appropriate thing where both these actions are fruitfully happened. That is cascading as well as cataracting takes place in a fruitful manner. So two different mechanisms. In the cascading portion, it is mostly abrasion, and the cataracting, it is again impact. Okay. Now comes this is a ball mill rod mill hybrid circuit, which generally in industries people use. Okay. Now when you go, what is the improvement in here? Here we are using charge as agate balls or manganese balls. Okay. Here wear and tear is very significant. So what happened is the development of autogenous and semi-autogenous mills. In this autogenous and semi-autogenous mills, they use some of the hard rocks present in that ore body itself as a grinding charge. So what will happen is your input as balls, which we are using grinding media, that reduces significantly. Okay. So this is a development of autogenous and semi-autogenous. In autogenous, it is entirely the ore particles, bigger size hard ore particles. In semi-autogenous, you reduce some of the charge, that is the metallic charge, and put the ore as additional one. That is in the semi-autogenous. And further development in this is stirred mills. Okay, in these stirred mills, what we have is you have an impeller also inside. Besides the metallic balls, you also have an impeller which gives a vigorous reaction. Okay, then by virtue of this, the generation of fines is very effective. This is very successful in ledging cores, very extensively used. And the design is in such a way that the energy savings can range from 30% to as high as 50% compared to a traditional mill. When you use a stirred mill in a circuit, the energy savings are better compared to what you get the same particle size by using the ball mill rod mill combination or rod mill ball mill combination. Okay, that is the development in this particular thing, and they are especially suitable for ultra fine grinding. Okay. Now once you do this grinding, there is another way of reducing the particle size, that is the grinding aids. Grinding aids are chemicals like sodium silicate, sodium hexametaphosphate. These things absorb on the particles and will not allow two different particles to come closer than certain distance. So what will happen? There will be complete dispersion of material within the fluid. Not only that, the grinding aids also helps in reducing the rheology within the system. Once the rheology is suitable for appropriate grinding, okay, the grinding action will be more fruitful. So what we are looking at, as I have given in the initial slide, there are three criteria. First thing is to generate fine particles effectively. What are the different things? New equipment, which we have seen here. Second thing is change in the circuit formation, that is use of autogenous and semi-autogenous mills. Even they can be combined with the conventional mills also, depending upon the ore characteristics. And third thing is using of these grinding aids. So these grinding aids also helps in reducing the rheology, and making appropriate distances between the particles because of the electrostatic charges developed, and help in better generation of the fines. Now, let us say after you grind a material, okay, now all particles are separated. All particles are separated. How do you separate the mineral of interest from the other? As we have seen in the one of the beginning slides, we can use different properties of the minerals, physical properties of the minerals. We can use size, we can use shape, we can use the optical properties, we can use radioactive properties, we can use the specific gravity properties, we can use magnetic susceptibility differences, surface chemical differences, electrostatic differences. All these things can be used for separation of one particle from the other. So if you come to the separation methodology, wherein we are using these specific gravity based differences between two minerals, that is called separation by gravity methods. Okay. Now let us see. In this particular thing, when you put any particle in a column of liquid, because most of these operations are wet operations, that is, you use water as a medium, mostly water as a medium. Dry separations are not taken, so far no development has taken place in a significant way, except in very few industries. So once you put a particle in a column of fluid, it is subjected to different forces. One is the gravitational force, which always comes down, okay, and then opposing this will be the buoyancy and the drag forces. So depending upon the equilibrium between these three forces, there will be the settling velocity of that particle in that column of liquid. So that is well defined by Stokes equation in our chemical engineering. Okay, chemical engineering, that will give you the complete. So once this is a basic principle. And how does the stratification takes place? Based on the specific gravity, it essentially takes place by three. One is this differential acceleration, then hindered settling, and interstitial trickling. Okay, this is how the stratification of the particles takes place. And these three mechanisms are severely dependent on both the density and the size. Both the density and the size, both the properties influence on these three ways of stratification. After this, there is something called flowing and thin film concentration. This flowing film concentration and thin film concentration are related to shear based separations of the particles. Okay, shear based separation of the particles. Now you can see pictorially representing, once you put particles of different density and different sizes into a column of liquid, the most heaviest one will be traveling fast. Then comes the heavy and bigger size one, and heavy and smaller size one will be following it. Then comes the lighter size particle. That's how the gradation takes place. But once they travel to certain distance, all will be forming a pack. Once they pack, this is called hindered settling. So initially, at the start of the cycle, it is free settling, but when all the particles come into closer zone, it is hindered settling. Once it comes to the hindered settling, the density of this particular zone will be equal to the density of the solids as well as the density of the liquid put together. Initially, all particles are separated, so it is only the particle thing which dominates. But once it comes to this particular hindered zone, there will be mixture of both. It means it's the pulp density which influences the settling of the particles. There again some segregation takes place. Once they come to the bottom portion, it is called consolidated trickling. In the consolidated trickling phase, all the heaviest particles will be there at the bottommost layer, but in between the heaviest particles, there will be some voids. Through those voids, whatever heavy small size particles will percolate. So the bottommost layer will be the fine heavies. That will be followed by the coarse heavies. Then there may be some mixture of coarse lights also here, because once all the fine heavies get to the bottom, there will be still some space left over. There comes the fine light, smaller size lighter particles. Then comes a bigger size light particle. That is how the stratification takes place in this gravity separation conventional method. Okay, now coming to the flowing film and thin film. When you have movement of liquid, okay, over a deck, static deck or a movement deck, then at the bottommost zone, the velocity of the liquid will be very, very low because of the frictional force between the surface, hard surface and the liquid. But as you go up, what happens? The fluid velocity will be more. So what happens is there will be combination of the stratification as well as the thin film concentration taking place in a plane zone. Because of stratification, these type of say arrangements will be taking place, and because of this thin film concentration, the lighter particles will be thrown out of the zone of separation because their velocity is more and these are lighter particles that will be shifted fast away from the settling surface. So that is how the stratification takes place. And when it comes to the other one, flowing film and thin film, there is another thing. Because of the movement of the deck, there is a shear force developed. The shear force acts perpendicular to the surface. So that's how the stratification takes place also by this mechanism, right? So these are some of the conventional equipment which we use in the gravity based separation. First is spirals. In these spirals, we have combination of both stratification and the shear force because of the movement of the fluid or the slurry in a circular fashion. The shear force also develops. Okay. Then comes the jigs. In the jigs, it is mostly the stratification takes place. Here, the shear force also plays along with stratification. In a jig, it is exclusively the hindered settling, interstitial trickling, and differential acceleration. But when it comes to the table, both the things keep happening. Here, what happens is once you feed the material at the feeding zone here, okay, feeding zone, there is a pattern here. This is called refills. In this refill zone, the jigging action will be taking place. Once the stratification happens here, it comes to the plane zone. In the plane zone, it is mostly thin film concentration, right? So combination of both these mechanisms happen in gravity separation, right? That is how it happens here. Now these are all the conventional gravity separators where only one times the gravitational force keep acting. Okay, but this will be effective only up to certain particle size. You can see here, if you spirals, these are effective only up to 50 microns. Down lowest size I am telling. When you take a shaking table, that is also almost slightly less than that, 30-40 microns. Similarly, if you take the plane table, it is much coarser. It is about here. So all these things are 50, say, if it is lower than 50 particle size or 30-40, it will not be effective. In such cases, we have to amplify the force of gravity. How do we do that? That is called centrifugal separators. So each of these conventional machines have been transformed in a different way to the centrifugal separators. If you take a table and make it into a folding this thing, it is called multi-gravity separator. Similarly, in jigs, we got centrifugal jigs. Like that, each one of them have transformed to centrifugal separation. Let us look at one of such mission that is called multi-gravity separator. This multi-gravity separator, the name itself says, it generates 11 times the gravitational force because of the motions, centrifugal motion of the drum. So here, each particle is subjected to different forces. One is the centrifugal force, other one is the gravitational force. Opposing them will be the wash water as well as the normal force that is developed on the deck. That is how there is segregation of the particles from the minerals of interest to the waste or lighter minerals, right? That is how the separation of the minerals take place, and it gives as high as 11 times the gravitational force. This is dependent on the diameter of that particular drum as well as the rotational speed. Obviously, when you say centrifugal separator, the diameter as well as the rotational speed, both these things matter much. So that is how it happens. Suppose you take 0.5 meters and n, that is rotational speed 200, it gives 11 times the gravitational force. You can use that equation, Fc by Fg is equal to that, right? That is how many times over the normal gravitational force that centrifugal force will be developed. That can be governed by that equation. Next, another development is Nelson concentrator and the Falcon concentrator. This Nelson concentrator gives almost 60 times the gravitational force. Here what you do, the difference between this as well as this one is, here it is horizontal axis. Whereas in a Nelson concentrator, to see it, it is a vertical one, vertical rotating bowl. So you feed the material from the bottom at very some given speed, then this bowl will be rotating. The separation actually takes place in the refills here. You can see refills are there. So once you put a material and rotate it, then obviously it goes to the periphery of that particular thing. Okay. Then how does the stratification takes place? There will be injection of fluidization water from the sides. This particular water discriminates lighter one from the heavier one. So obviously the heaviest particles will be along the surface and the lighter ones will be washed away. That is how the lighter particles go out here and the heavier particles can be picked up to the required zone. Okay, this is Nelson concentrator. A development in Nelson concentrator is Falcon concentrator. This is a development in this. What actually Nelson concentrators are batch mode. They are not continuous. After you do the required separation, the refills are filled up with the required material. You have to stop it for a moment, then discharge that particular, drain that particular thing and use it in the next cycle. But the further improvement in this is the Falcon concentrator. This Falcon concentrator gives as high as 300 times the gravitational force. 300 times the gravitational force. So here you can see a small development also they made. Instead of having the refills from bottom to the top, there is one lean zone and then there is a separation zone. This is the fluidization and retention zone. Okay. So as the feed falls over a fan here, there is a fan, it disperses the particles, and here actually the stratification. Whatever happens in a jig or whatever happens in a table between the refills, that happens here. Then it goes into the concentrator. These were the equipment which have come under the shear force based separation techniques. Okay. So we adopted that for uranium. Uranium you must be knowing very heavy. So what happened is when you use the gravity table, we tried to recover uranium from copper plant tailings which are extremely fine. So it was effective only up to this size. In fact, it is effective only up to here. But when you use the Bartels-Moseley separator, it is a sort of shear force based. You have a deck and you have a rotating eccentric motion underneath it. So what happens is when it keeps on rotating on a very on a belt, then what will happen is the normal force develops and segregation of the particles takes place. So because of that centrifugal force, extra gravitational pinning is there, and this particular curve, recovery curve, has enlarged to this extent. More particles are getting captured. This is a factual thing. Okay. Now, when you look at this particular graph, you will get to know the continuous lines shows for 1g and this dotted line shows for 200g. If I take a particle of 1 mm diameter, what will be its settling velocity when it is what I will say in a normal 1g and at 200g, you can see that whatever spins are there, they get disoriented. So for example, you take iron core on which these wires are, this electrical energy is passed, current is passed. Then after certain stage, it attains saturation and it may not be effective in capturing of the particles. So under such cases, what is to be done? So the magnetic force acting on a given material is dependent on two things, applied field as well as the gradient. Both these things, the product of this will give you the magnetic separating force. So there is a limitation on H. You cannot go beyond certain limit, beyond certain level. So on such cases, you can manipulate the gradient. Gradient is nothing but if you change the size of that particular material size, then the flux increases. That is the number of lines for a given dimension or for a unit length that will become much closer. Therefore, the gradient from, suppose if I have pen and this thing, if you have a magnet of this shape and a magnet of this shape, here what will happen? All these forces will be distributed like this. The magnetic lines of force. But in this case, what happens is there will be concentration of these lines here. So what will happen? The flux changes. Once the flux changes, the capturing capability will increase. So these are very broad ones, but you can even have a fine wire also. Wire, dehomogenized wire. I will show you in the next slide. You will understand, or it is here. No. So what happens is, depending upon the diameter of the wire, the gradient can be increased further. They are called high gradient or high intensity magnetic separators. If you are using 2000 Gauss or to around 2000 Gauss or less, it is called normal magnetic separator, low intensity magnetic separator. If anything is above 2000 Gauss, it is called high intensity separator. If you further change the geometry of this particular separating mesh or whatever you say, that body element, then it is called high gradient magnetic separator, depending upon the type of structure you use in the separating for this one drum. So you can see here, this is rare earth permanent base magnet based separator. Now, when you go to this particular thing, as I was telling you, this is high gradient magnetic separator, where the equipments are, the separating zone is having lot of wires. So because of this geometry, it will help in increasing the gradient. Therefore, the capture probability increases. Capture probability of finer size particle will increase. Now here you can see development in this is, even in this high gradient magnets, where also once you increase the current, the resistance also increases. So what happens is the effectiveness will come down after certain stage. There comes the superconducting high gradient magnetic separator. Here we use superconducting wires like niobium tin, okay, niobium titanium. These are some of the superconducting wires which I have shown you, niobium titanium and niobium tin wires. This will be able to give a field strength of 3.5 Tesla. 3.5 Tesla. To that extent, it can give the field. And the beauty of this is it can work without any problem. No heating will be there. But only disadvantage is the so-called superconductivity is present at sub-zero temperatures only. Very low temperature, liquid helium, liquid nitrogen temperatures. It cannot be operated under normal room temperatures. So this type of technology has got some limitation. This is used only in places where removal of very fine size material, especially in the clay industry, removal of ultra fine size iron is taken out, the value addition is significant. There only the economics is sustained. Otherwise, it is very difficult. Similarly, this can be used in removing some of the nuclear effluents. Nuclear effluents, after putting in the reactor, they do contain ultra-fine size particles, which are very detrimental if they are released to the environment. So in such cases also, these superconducting magnets are used, which are helpful in removal of those particulate matter. Okay, but there is quite a good success in use of these high gradient magnetic separators in the industry also. Now comes the other separation method, that is called froth flotation. So we have seen the gravity based separation, we have seen magnetics susceptibility based separation, then comes the separations based on the surface chemical differences, surface chemistry differences. So what is froth flotation? By definition, it is a process for selective separation of hydrophobic materials from hydrophilic. What is hydrophobic? Hydrophobic means it is having averse to water, absorption of water. Hydrophilic means it is having highly polar surface. Okay, water molecules are attracted towards it or present on that particular thing. So these are called hydrophilic and hydrophobic. Why we are saying hydrophobic and hydrophilic is the attachment, froth, flotation. Flotation means you are levitating to the surface using air bubbles. The absorption of air bubbles on the particles will be facilitated only if the surface is hydrophobic. If it is hydrophilic, the surface tension forces will not allow the air bubble to sit over the mineral surface. So what we can do, there are two ways. Some minerals, for example, you take sulfides, molybdenite or chalcopyrite. One, if the cleavage plane is across the sulfur, then the surface is hydrophobic. But for in the case of oxide minerals like cassiterite or wolframite or some other mineral, rare earth minerals and all, it is highly hydrophilic. So in such cases, you introduce the hydrophobicity by selective adsorption of an collector molecule. What is a collector molecule? A collector molecule is such a chemical structure which has got a polar functional group attached to a hydrophobic extension. So this polar end of the molecule, organic molecule, will sit over the mineral because of the chemical forces between them that can be ionic or it can be covalent or coordinate covalent, and the hydrophobic one will be giving the required hydrophobicity to the surface of the mineral so that the air bubble can sit over that particular adsorbed thing, induced material, that is induced hydrophobicity. So you can see here physically, this is the mineral and this is the collector. This particular thing is a hydrophobic chain and this is the hydrophilic chain. This particular thing has got chemical affinity to the surface of this particular mineral, maybe to the metal ion present in that or to the different whatever is disposed on the surface of that. So once it is adsorbed, you introduce the air bubbles. But air bubbles as such also will not be able to bond with the collector molecules because there will be some residence time, that is called induction time. The induction time should be so planned that the collision is fruitful. So in order to have fruitful collision between the air bubble and the hydrophobic chain, we also introduce what is called frothers. These frothers are nothing but they are also organic molecules only, but they have lesser polarity or no polarity, but they do have this particular hydrophobic length. So this hydrophobic thing will help in van der Waals interaction between the two tails. Van der Waals interaction is non-bonding forces between the two. Like we know ionic bonding, like we know covalent bonding, there is also something called van der Waals bonding. This van der Waals bonding is a non-bonding interaction like hydrogen bonding, very weak one. So that will help in the tail of the hydrophobic chain having interaction with the hydrophobic part of the collector, latch each to the and helps in levitating to the surface because air bubble moves to the surface by the buoyancy force. Therefore, the hydrophobic mineral particle is brought to the air-water interface. Besides this levitation, the frother also helps in reduction of the surface tension on the surface because the air bubble should remain stable on the surface for some time so that it can be scrapped and taken into the concentrate lander. If it has to remain there for some time, the surface tension should be minimum. So the frother also helps in reduction of the surface tension on the froth structure. Having a suitable froth structure so that whatever bubbles come to the surface, they remain there for some time so that it can be scraped into the concentrate lander. Right? This is how it takes place. Now, if you take flotation, it is an interaction between three different components. One is the chemistry part, as you see, induced hydrophobicity. That means the chemical factors come into picture. Chemistry of collector, chemistry of the frother, and chemistry of the modifier. What is this modifier? Modifier is again a chemical reagent, which what it will do is it generates some sort of charge on the materials. Suppose you have silicates which are interfering with some mineral of our interest. So what they do is they introduce these modifiers. These modifiers sit on these silicate minerals and give more charge on them. Then what will happen is it will remain highly hydrophilic and will not have any chance to interact with the collector molecules so that the collector is more and more concentrated or focused on the minerals of interest. Okay, so it will channelize the collectors towards the minerals of interest and leaving the gang. So essentially, these modifiers do the action of dispersion, that is moving the particles, each of them away one from the other. Also, it will control the depression of the flotation, dispersion and depression of the flotation. It is depressing certain things and it is allowing something, so collector molecule, to sit on the desired minerals to float to the surface. Okay, so that type of depression it is doing. It is also dispersing so that the collectors or the reagents which we are adding go to all the mineral particles and do their needful job. Okay, that is one thing. Modifier also has got some other effect. Suppose you have two sulfide minerals, right? You add some modifier, metallic ion, so that one sulfide can be distinguished from the other sulfide. That is why how you do the base metal separation. You add some copper. Copper itself can act as a modifier, some copper compounds like that. That copper will interact with sphalerite or galena or something, and it will nullify the sulfide surface. It will not allow the collector to absorb on that, thereby allowing among the two sulfide minerals, one to float and one to get depressed. So the modifiers can be inorganic molecules, it can be organic molecules, right? Doing all this type of action, that is, it modulates the flotation process. So these three, the chemistry part. Next comes the equipment, because ultimately you have to generate the bubbles, and the generation of bubbles is a mechanical feature. So the equipment design, cell design. Okay, cell design means, what I am going to say is the length, or the height, so that the bubbles go to this particular thing. The residence time within this reaction zone is properly controlled. So the cell design is important, and the agitation speed. Agitation speed is important because I told you the interaction of the frother to the collector is by very weak van der Waals forces. Even here, after everything is happening only for a few minutes, no, it is not kept for longer time, so that the complete interaction takes place. You are not allowing for that. Kinetics is very important. Therefore, what we are doing, we are allowing the entire process to happen in 5, 10, 15 minutes. So whatever little linkages are there at each place, they remain intact. They don't get disturbed by the shear things which is happening, because there is vigorous agitation. Because of this vigorous agitation, whatever is got attached should not get detached. Therefore, the agitation, that is very important. Then airflow, how you are introducing the airflow into the system. Are you using finer air bubbles or are you using coarser air bubbles? So the generation of rotor and stator, that is, this you can see here, this is called the impeller. In impeller, there is something called a rotor and a stator. The outer one is stator casing. So once it moves inside, there is shear of the air that is introduced and the bubble size is dependent. Okay. So these three things, the airflow, the agitation, the cell design, come under the equipment components. And comes the operating conditions. The operating conditions also you are responsible for successful flotation. One is the feed rate, that is, what is the residence time you are giving for the material within that reactor. If you consider the cell as a reactor, in order to control give the required residence time, you have to have proper feed rate. Mineralogy, of course, that is what is dictating the entire thing. What is the mineralogy? What is the mineralogy of the mineral of interest? What is the mineralogy of the gang material? Both these things have got indirect influence on the all these chemical features. Then comes the particle size. Finer particle size have different velocity in moving here. Their inertial forces are different. Coarser particles, their inertial forces are different. The inertial forces again influence the residence time, appropriate induction time. It is controlled by the particle size of the bubble as well as the particle. So it moves within the system because everything is dynamic in nature. So the particle size is important. And then pulp density. I was explaining this. And then the temperature. Why temperature is important? Because some of the collectors absorb on the minerals by physical forces only. Okay, some absorb on the mineral by chemical forces. So it is called physisorption and other one is called chemisorption. right? So if the activation or the that energy of interaction is more than 40 kilojoules per mole, it is called chemisorption, the absorption, this thing. If it is less than that, it is called physisorption. So once you have temperature, always any process where physisorption is the controlling factor, temperature will disturb the physical absorption. It is physical in nature. Okay, it will be there. But in a chemisorption process, temperature helps in better attachment of the collector molecules to the thing, because we know there is the hump type thing, no? When you have activation energy, you have transition state, and then it goes to the stable state. So all these things, the chemical way of adsorbing of a collector on a mineral are influenced by this temperature. So all the things should be properly manipulated or properly configured to have successful flotation. Got it? Now, now you see here, the particle bubble collision is, particle attachment to the bubble is a very, very complex equation. You can see what is dependent. Particle bubble collision, PC, is depending upon the interceptional, gravitational and inertial factors. These are the three things. Interceptional means both of them should come into the vicinity. Then only this thing. If bubble is not there in the vicinity, nothing. So it should have that in the vicinity, both the things. Then gravitational. That is why particle size is important. Also, it has influence on the bubble movement also. And then inertial factors. So inertial factors, because that will dictate the residence time. If something is moving slowly, this one also is moving at appropriate speed, then both will have enough time for interacting. Otherwise, fellow will move fast, this fellow will move slowly. The chances of collision will be very, very limited or unsuccessful. PC, that is collision, increases with increasing particle size and decreasing bubble size. Okay, the collision will be more if the particle size is more, and because if the bubble size is less, its movement towards the surface is also less. Bigger bubbles travel faster to the surface. So appropriate bubble size should be there. And then fine particles have low probability of collision with the large bubbles. Particle attachment to a bubble, this process is determined by hydrodynamic and surface forces of the particles, because you also have to be aware that there is lot of electrostatic repulsion between the particles that will not allow the collectors to come anywhere near it. So it will go through something called a standard Lennard-Jones potential field. Okay, all of you must be knowing it. Okay, so when it comes to the closer and closer, lot of electrostatic repulsions will be there. Once it surmounts that, then only the bonding forces come into picture. Understood? So that is why this particle attachment to a bubble is influenced very severely by these forces which are coming in close range. At a distance, it is the mechanical, this bubble is here and a particle is here. Mechanical forces will bring them to the proximity. But when they come closer, the attachment is influenced mostly by the chemical forces and electrostatic forces. Right? So that is why the hydrodynamic and surface forces. What I mean by surface forces is that chemical forces only, charge forces, hydrophobic forces, all those things. That is the thing. So ultimately it is the thing. Now, to float finer size particles, people have devised different equipment. Some of them I will just show you. This is the conventional flotation cell. The bubble diameter is 0.7 to 1 mm. Average bubble diameter is 0.7 to 1 mm. Suppose you take a column flotation cell. This is meant for finer size particles like finer molybdenate, all finer particles. In this case, the bubble size is how much? 0.3 to 0.5 mm. How do they control the bubble size here? You have a frit here. The frit is having porous frit. The frit is having small holes. So once you introduce air, that will be split depending upon the diameter of the frit. That is how the bubble size is controlled. You also have electroflotation. Electroflotation. Here what happens is two electrodes are there and the water is electrolyzed. During this process, there will be generation of hydrogen bubbles and oxygen bubbles. These bubbles, electrically generated bubbles, are having a diameter of 38 to 68 micrometers. So extremely fine bubbles. But only thing we have to see is whether the oxygen bubbles will have any interference in the separation process. They may oxidize the mineral. So because they're fine size bubbles, they are quite active. So whether it will have any influence on the surface charge of the material, that we should be conscious. But it is quite a successful thing if the particle size is very finer size particles, finer bubbles are generated. Okay, these are some of the developments and things which we need to use for finer particle separation. Now, even see earlier days we are having some standard methods, that is you use xanthates for the sulfide minerals, you use oleates for the oxide minerals blindly. Whatever may be the oxide, we use oleates. Whatever may be the sulfide, you use xanthates. We are not making any distinction in a broad way. But the development, understanding in chemistry, and the development of theoretical chemistry, molecular modeling, molecular architecture, all these things have led to designer molecules. These designer molecules means you understand the disposition of the metal ions in the crystal structure of a given mineral and design your molecule with appropriate anchoring points. Okay, appropriate anchoring points, not only the type but also the interatomic distance between these two anchoring points, so that it perfectly matches with the disposition of the metal ions on the surface. So these designer molecules is a development that is called molecular recognition technology, MRT. These are the things which we need to have more and more use in our mineral processing industry, so that we will be successful in tackling the finer size mineral particles or these so-called critical minerals sector. So what does it happen here? Again, it goes to the fundamentals. We all have studied in our intermediate and all hard soft acid base theory, HSAB theory. We all must be knowing it quite. Okay, it goes like that only. Pearson's hard soft acid base theory. So in this, the HSAB principle states that hard acids, that is electropositive metal ions with less polarizability, prefer to bond with hard bases, and soft acids prefer to bond with soft bases. That means any metal ion which is having polarizable electron cloud will also interact with the corresponding organic molecule wherein it can be polarized. Organic, that is you say that element which have polarizable cloud, right? Again, it goes back to the bond energy calculation. There is something called lowest unoccupied molecular orbital, highest unoccupied molecular orbital. If those energy levels are closer, the complexation takes place. It goes like that. Broadly speaking, it is this hard and polarizability. Okay. Hard bases include those reagents having oxygen and nitrogen as the anchoring points, right? Those molecules having oxygen and nitrogen, which are less polarizable. We all know oxygen is highly electronegative. So you cannot pull any electron cloud from the nuclear, the effect of the nucleus beyond certain point. So its polarizability is very less, very compact. Similarly, nitrogen. When you come to sulfur and phosphorus, they are having polarizable clouds. So these are called soft bases. Soft bases, right? These things will interact with corresponding hard acids, that is metal ion, which is having low polarizability. The soft ones will interact with those metal ions which are having more polarizability, right? Based on this, the chemistry and design of the molecules. Ultimately, if you see the different molecules available in mining chemicals, all are mostly nitrogen, oxygen, phosphorus, or sulfur. It goes around these four only, mostly. Now, you see here, you have alkyl hydroxamic acids. These are nothing but, again, oxygen based. Very, very selective collectors for rare earths. Then phosphonic acid. This contains oxygen as well as phosphorus. It is not only the anchoring point, but also the molecule, the element that is present linked to it. So that fellow will influence the dragging of the electron cloud from the endpoints. So phosphorus is present, or oxygen is present, or sulfur is present. That will have the entire chain. That is why it is called molecular architecture. It is not only the anchoring points, but also the molecules attached to that anchoring points. So they will have what we all know very well, induction forces. Induction forces and resonance, mesomerism, all these things are chemical nomenclature, which will have influence on the electron density on the endpoints, right? So that is the thing. Here it is phosphoric acid based things, which are quite extensively used for some of these tungsten, tin, even rare earths also. There is something called kupferon, which is containing nitrogen as the endpoint. So all these things. Now, these structures you will know. Molecular design methods offer an effective way for understanding the structure property relationship of the flotation collectors and developing new ones. How do they do this? See, as you see, the steps in this is the geometry of the reagent molecule is optimized first. Optimized means it goes to the most stable configuration. Optimized using the unified force field technique. That is one method of in chemistry, theoretical methods, unified force field technique, which will be useful in calculating the this energies, okay, interactional energies and all those things. That is one technique. So you using that technique, you have most optimized molecular configuration. A surface cell is again created from the unit cell of the inorganic crystal at its cleavage plane. See, there will be different cleavage planes in a crystal, 100, 010, 001, all those things. And every mineral has got one cleavage plane only across which the grinding takes place. Once you grind it, maybe predominantly 100 will be present, or 010 may be present, or 001 may be present. So there is a preferential cleavage plane. So you first decipher that, try to get that. Now you know what is the surface disposition of different metal ions on the inter distances between each metal ion in that particular cleavage plane. So that is optimized cleavage plane of that mineral crystal, and you have the optimized structure of the reagent molecule. Then on a computer you try to dock that particular thing on the surface of this and calculate the energy. After you get this, what you do is you try to change the structure of the molecule so that see, in order to get the required hydrophobicity, how much of extent of adsorption has to take place? Because that is also important. It is not that one molecule sits on the mineral and it levitates to the surface. How much hydrophobicity on the surface needs to be generated? So that again depends upon the steric interactions between the tails, that is the hydrophobic things. Okay, hydrophobic. Is it aromatic or it is what is it called? That linear one is called, can anyone tell? I forgot. The one is aromatic, another aliphatic. Aromatic and aliphatic. Okay, so that type of thing. If it is aliphatic, how much branching should be there? All these things influence the steric interaction on the surface, so that this fellow should approach the mineral surface. If it has to approach the mineral surface, the feather should allow it. Feather means that branching and all those things should allow it. So all these things they will manipulate on the, do the needful computation on the system based on that thermodynamic calculations and all, and generate the appropriate molecule. Once you get an appropriate molecule designed, you synthesize in the laboratory and then test it, see whether it is happening or not. So it has in fact given a very positive results. Very positive result. This is very important in the case of having designer molecules for solvent extraction of rare earths. Because you must be knowing, the most difficult challenge in rare earth separation is separating one rare earth metal ion from the other. Separating lanthanum from cerium, cerium from neodymium, because all have same charge and the ionic size is not very different from one to the other. Okay, broadly you may differentiate into what is that called? Lighter, medium and heavier rare earths. But within the lighter, how to separate? Within the middle, how to separate? Within the heavier, how to separate? It is very complex. So in such cases, we can switch over to these designer molecules. In fact, people have successfully separated fluorite, calcite and fluorapatite. All are having calcium, but still using this molecular design and making a molecule called IMPA8 with this structure, they were able to successfully separate fluorite from the rest too, because the interaction energy is lowest for this compared to the other two. You see what is the flotation performance? At very low concentration, fluorite was successfully separated. This is the recovery. Fluorite could be separated at very low concentration. Whereas to get equivalent recovery of calcite, you have to have very high reagent. So by using the concentration of the reagent, you can separate minerals which are having same metallic ion, calcite, fluorite and fluorapatite, right? That is how this molecular design of molecules helped in separation of individual minerals. Now, now comes again another thing is, see, ultimately what for we are working? Can anyone tell? All our labor of lecturing on this is for what? Mineral extraction. Mineral extraction of what type? Not rare earth. I'm not bothered about rare earth. I'm only quite often quoting rare earths, but I'm not bothered about rare earths in general. You are telling very generic thing. Huh? I have given that indication in the beginning and I'm repeating quite often. Fine particle sizes. Because I told you all these critical minerals, most of them are very, very friable and they go into the fines quite often. So in order to get those fines, how to get those fines and separate them? So different this is another technique. Surface. See, in the flotation, we are generating appropriate, what is that called, molecules, which can adsorb on it in a chemical fashion using chelate type of things. Now there is another method of separating the particles, finer size particles, by something called agglomeration. Agglomeration means you have 10 particles of chalcopyrite which are present in 2 microns. Okay, you want to separate it. How do we do it? There are two methods. Either you should have a separating force which can interact with that 2 micron fellow, or you can bring all the 2 microns at a single place, make it a bigger one and allow it to settle down. That is called flocculation. That is called flocculation. In the flocculation process, what we have is, you have a backbone, organic backbone, now hydrophobic one, onto which you put graft the functional groups. Functional groups means they are the operating part. So that is what functioning is. So this functioning part of that particular backbone will go and sit on that copper. Like that, this chain will see to it at different portions, these anchoring points are there. All these anchoring points will interact with these fine sized particles, and once all these particles are anchored by the functional group, then it gets coiled automatically, because the bulkiness increases, no? It gets coiled. Once it gets coiled, that is called a flock. Once a flock is formed, naturally its density increases. Once the density increases, it settles down. Once it settles down, then easier to separate. So this is again called surface chemistry based separation using the technique of flocculation. Okay, using the technique of flocculation. So again, the concept goes back to the initial design of molecules, design of all those things only. But the methodology is different. Here you are having a polymeric backbone grafted with functional groups, selective functional groups, which have interactional ability, chemical interaction ability with the finer size particles, which helps in anchoring to them and coiling, thereby increasing its density and settling down. Right? This is called flotation. This is another method of separation. You can see here physically. Again, here what is important is, I just want to tell, the surface charge of the mineral is very important. Equally important is surface charge of the molecule, because once you put any organic molecule with some functional groups, their ionicity will depend upon the pH of the system. Some will be having cationic charge, some will be having anionic charge, some will not have any charge. Okay, they are called amphoteric in nature or neutral in nature, right? So that is one thing. That is the molecules. When you come to the mineral, based upon the dissolution of the surface metal ions into the surrounding liquid, there may be a positive charge, residual positive charge, there may be a residual negative charge. Okay, positive charge on the surface or negative charge on the surface. Again, that is dictated by the pH of that particular medium. So what happens is, if you want, or if you have a collector which is predominantly acting on the physical forces or Coulombic forces, then the charge between the mineral and the anchoring molecule should be opposite. Then the Coulombic interaction is fruitful. If you have chemical forces acting on that interaction or the flotation or flocculation, then no matter what is the surface charge, it interacts with this because it goes beyond. Again, it goes to the Lennard-Jones potential. It comes over that bottom and approaches it at much closer proximity. There happens the covalent bonding and all those things. So charge is a surface phenomenon. Okay, charge doesn't matter there. So the pH of that particular medium of separation is very important. By manipulating the pH or the solution chemistry, you can also change the nature of interactions, bring about the selectivity in any of the surface chemistry based separation. Okay, same, go back to the grinding. Grinding media also we introduced some grinding chemicals. What do? They adsorb on the minerals and then help in reducing the viscosity, help in dispersion. All these things are interparticulate forces only. So that is how the surface chemistry has got its manifestation not only in flotation flocculation but also in other separation techniques like your grinding. Though it is not a separation technique, it got role in tabling. Tabling also sometimes agglomeration takes place. In order to have proper dispersion, you add some sodium silicate, right? Similarly, the pH of the medium, you control the pH of the medium so that effective separations take place, proper charge develops, and then there will be a sufficient dispersion of the particles on the table. Okay, that is a thing. It has got role in magnetic separation also. So everywhere the surface forces have a functional, what I will call functional activity, functional or that activity in separating the things. So flotation is enlarging the particle and allowing it to separate. Now, how do we separate? Actually, it has formed a flock. How do you separate it? Again, go back, put that particular flocculated suspension on a gravity table. Then what will happen? The larger particles are better captured on a table than finer particles. We know very well. You can separate. That is called, where is that? Gravity concentration of the flocks. Gravity concentration of the flocks. You make flock and then use the gravitational force for separating them. And then you can even have flock flotation. I was telling you the bubble size and the size of the particle have severe dependency on the success of any flotation process. Instead of shifting to the most modern column flotation or modern quadrant flotation or electroflotation or those things, you can use the conventional cell itself. By forming the flocks where larger particles are formed, you manipulate your impeller speed, your air bubble size, use this flocculated suspension into the conventional cell and float it. Larger particles can be easily floated. Okay, that is called flock flotation. And all these things have shown quite a good success. Only thing is, its applicability was very limited because earlier we are having high grade and reasonably coarse sized materials. Today we are restored with fine grade lean tenor materials. So you have to go for these things quite extensively. And that is why I keep again insisting mineral processing is more of shop floor expertise. Shop floor expertise. By just sitting on the table, you may be able to design a molecule, but ultimately you have to see whether it works there or not. And if it has to work, then you have to manipulate all the operational conditions. Who will operate? Who will do the operational conditions? A layman cannot do it. A technician cannot do it. That can be done at least in the initial stages to establish or to validate your thing by only a person properly trained, properly skilled. Then only you will be able to distinguish one from the other and see what is happening there, right? Now, as we know very well, we have got a lot of issues with the conventional flotation collectors also. For example, you take xanthates. They are not actually, when you leave the effluents to the environment, sulfides are not very eco-friendly or environmentally friendly. So what we have to do, those things also need to be recycled, and recycling of chemically adsorbed or chemically disturbed molecules is not so easy. Recycling can happen if the original person or original molecule is not disturbed in its structure, in its activity and all those things. But if it is getting disturbed, recycling is very difficult. So it is all once go only, once through only. So xanthates, there is limitation. And we also have studied that, or rather seen that once you have finer size particles, the reagent consumptions are more, because there will be so many things which consume the reagent. So if you want the required one to go to the required material, you have to add more, because the other people are saturated, the required one needs more. So reagent consumption will be more. Once the reagent consumption will be more, when you are treating low grade ores, only some part will be effectively used, rest will be thrown to the environment. So when you cannot handle those effluents, it will be a big problem. Many of these heavy metals are present in sulfidic form. Some are present in oxide, some are present in sulfide, or a mixture of both. You take Malanjak copper ore. People may be knowing Malanjak copper. We are not very successful in that copper deposit, because the reason is, not only it is containing pure sulfide of copper, it is also having semi-oxidized sulfide copper minerals, right? So what is happening is, the xanthates alone are not able to pick up the material. There will be something left which is partially oxidized or in completely oxidized form. So we are using synergistic collectors. What is a synergistic collector? Combination of two collectors. You are using xanthates along with that hydroxamates. So these hydroxamates have got affinity for oxides, xanthates have got affinity for sulfides. Together they will be able to float the thing to the surface. Okay. So why I am telling this is, extensive use of xanthates, indiscriminate use of xanthates without understanding the mineralogy is also detrimental, because the effluents contain a lot of this. That is why slowly the transformation is going for biologically or environmentally suitable molecules or collector molecules. One of them is the biosurfactants. Even in the chemically synthesized molecule, you can have something which can be properly degraded and environmental friendly. But the one which we can easily put hand on is what is available in the nature. They are called biosurfactants, bioflocculants, bioleachants, right? These are the things. Why? Because if you see the structure of the amino acids or proteins in that, again they are also containing these carboxylic end groups, these amine end groups, these things only. We are using same thing for our separation as per HSAB principle. So why not we use that one which is available in the nature? So then comes the advent of biobeneficiation and bioflocculation. Okay, you may not be able to isolate the required organisms, required things so easily, but nowadays the chemistry has developed to such an extent, people are able to synthesize those things in the laboratory and use it in the field. Okay, that is happening because the operative part of that particular bio thing is only some portion of it, not entire thing. So you see it, you mimic it in the laboratory and design that and use that. That is how it is happening. Okay, that's why today, if you see, many of the mining chemicals have shifted from the conventional mineral acids to organic acids. Today you use, I mean, you see in your publications use of citric acid, use of oxalic acid, use of something like that, right? Or protein based structures for dissolution or for flotation or for any such thing, because its biodegradability is more. Okay, so that is how we are taking inference from. If you are successful with this, you can use the biologically available things, bioleaching. That is called bioprocessing of the minerals. It is also on dumps and all, especially on dumps, lean tenor ones. If you are not very much concerned about the kinetics, you can use these biomolecules. That is one of the hindrance in using bioprocessing. Their kinetics is very slow. Now there is even development in this bioprocessing also. We have got bioreactors, wherein the kinetics is slightly enhanced by design of that reactors and all those things. So it's called bioreactors. Otherwise, conventionally, we are using these biomolecules or these natural products only on copper dumps or any sulfidic things, because it works only in the acidic environment, most of these things. Okay, so that can happen only in that such type of mineral assemblies, waste dumps or something like that. So some of these things are, these are the various organisms. You can see here, the difficult to spell out these things. Okay, acidothioBacillus ferrooxidans, rhodoceus opacus, all these things, Bacillus pumilus, all these things, and they are used for different minerals, separation of these minerals, right? So it is quite successful. And what I can say is, much of the research activity in US and all is focused on taking information from these bio things and making similar molecules in the laboratory and using them extensively, right? That is how it is happening. Now, again, coming back to the mineral processing, we have seen this physical separation overview. Let us see what is the chemical extraction. Okay, so I will just take some. Yeah. This one was how much time? 45 minutes? 1 hour? Huh? Oh, great. So I think we can start. All are there now? Any missing? Anyone missing? Here, someone was sitting here. Yes. All right. Okay. So anyway, again coming back to our this thing, we have seen in depth this. Uh, oh, it is there. Correct. We have seen in depth this physical separation part and what are the various techniques we adopt for separating the particles, okay, in a given ore, with more emphasis on finer size particles. How do you modify the separating equipment to tune for the capturing of finer size particles? Now, up to this stage, we can call it as a pre-concentration. Pre-concentration means something is present at 0.1%, you have brought it to 5% or 10%, or if you are successful 15-20%, not beyond that. So that is why it is called pre-concentration. Once you pre-concentrate, you have not disturbed the mineral as it is. You only physically separated the required from the unwanted. Now if you want the metal ion, a purified metal ion, which goes to an extent of about 60-70% as an element, then you have to do chemical processing also. So in this chemical processing, as I was telling in the beginning, we have got hydrometallurgy, pyrometallurgy, electrometallurgy and biometallurgy, bioprocessing. The 4 different techniques are there, but most prevalent is hydrometallurgy, because pyrometallurgy also has got lot of negative attributes, except in ferrous industry you leave them, but in this non-ferrous sector we adopt for chemical, this is hydrometallurgy only, aqueous processing only, because there is a lot of release of these toxic gases, the energy intensity is more and all. Whereas in hydrometallurgy, first thing is the requirement of those service things like energy or water or those things are to a great extent less. Further, the selectivity can be achieved better in hydrometallurgy than in pyrometallurgy. Okay, electrometallurgy can always be a complementary to the or rather supplementary to this particular technique. If pyro followed by electro will be there, hydro followed by electro also will be there. So electro is essentially for fine tuning the ultimate product purity. Okay, that is a thing. And bioprocessing, as I have told earlier, it is definitely useful, but it is useful only for a certain set of minerals and its kinetics is lower. All these things are there. Therefore, industrially we go for hydrometallurgy only, many of these things. Now, hydrometallurgy is a technique within the field of extractive metallurgy, for obtaining metals from the ores. It involves use of aqueous solutions for the recovery of metals, concentrates, recycling also uses hydrometallurgy extensively, recycling methodology also. Hydrometallurgy is typically divided into three general areas. What are those? Leaching, followed by solution concentration and purification, and metal or metal compound recovery. These are the three steps in that. Like we have in physical separation, comminution, separation by gravity, magnetic, or gravity, flotation, or flotation alone, like that. Here we will have leaching, for taking the metal of interest from the mineral into solution. After it comes into the solution, you again separate it further, enrich it further. That is called separation and purification. After you separate and purify, you put back as a solid form. That is called product precipitation or metal recovery or metal compound recovery. Those are the three stages in there. So, what is leaching? Very broadly speaking, leaching is a process of extracting minerals from an ore or mineral pre-concentrate by dissolving them in a suitable liquid, always called as solvent. Okay, not always called as a solvent. Then the soluble particles leached into the liquid phase, that is called leachate, leaving behind the passive material, that is called insoluble particles. So thereby you are getting the required separation happening here. Now, if you see the leaching, it essentially takes place by the following micro steps. One is you add a leachant and you have a solid particle, and then the slurry is formed. This leachant approaches the mineral particle. How does it occur? First, the reagents must diffuse to the mineral surface. It should travel to the surface of the mineral. Reagents must adsorb on the mineral. They first adsorb on the mineral. Then the chemical reaction takes place between the mineral and the leachant which you are adding, lixiviant which you are adding. Then what happens is the product of that reaction will be soluble. So it goes back into the solution. This product again should diffuse back into the bulk solution. So these are 4-5 steps involved in this particular one. First thing is reagents must diffuse to the mineral surface, reagents adsorb on the surface, chemical reaction should take place on the surface, reaction products must dissolve from the surface, and then reaction products after dissolving from the surface should go back into the bulk. Okay, because there is a thin film there, actually this reactions will be taking place. From the thin zone it should go back into the bulk zone. All these steps have got some what is called role in the efficiency of the process. So if you see, this is how you take simple. If you do it in a laboratory, it goes like this. You have the ore material, you have the reagent. This exivient or leachant can be an organic molecule, can be a mineral acid, or it can be a combination of both. You use quite often sulfuric acid, or you can use hydrochloric acid, or you can use nitric acid. These are mineral acids. Phosphoric acid also. In organic acids, we use lactic acid or oxalic acid or citric acid or whatever it is. Then when it comes to the combination also people use in different circumstances. So here there are three different mechanisms. One is the physical, another one is chemical method of leaching, another one is electrochemical method of leaching. In the physical method of leaching, you can see it is a process in which solid is leached in aqueous phase or water, and there is no chemical transformation. It is simple solvation, only hydration. That hydration will help in moving of the metal ion from solid phase to the liquid phase. Simply you take salts, sodium chloride, silver chloride, these things, simple physical dissolution. You put it in the water, solvation takes place, then the solid phase gets converted into the aqueous form or solution form. Okay, not aqueous, solution form. Now, in the chemical dissolution, actually the chemical reactions take place. You can see there. Here, the process is for covalent bond solids, mostly. That is for ionic solids. This is for covalent solids, covalent bonded solids, and takes place based on the neutralization or complex formation. That means the leachant which you are adding complexes with the metal ion. The resultant complex is soluble in the suspension medium. That's why it goes into solution. Okay. If you are by pH adjustment also, that is also chemical dissolution. You take aluminum hydroxide. when you put it in some system of some solution chemistry conditions, it dissociates into aluminum plus 3 and hydroxide. If you try to shift the system to more acidic thing, then the hydroxide keeps on taking away in the acidic conditions by the H plus ions, and the equilibrium will shift towards it. There will be more, what is it called, forward reaction takes place further, and that is how the dissolution takes place. As such, it is in the solid phase, but once you go into the acidic nature, acidic conditions, the OH will be consumed by the protons present in the system, and aluminum ion as will go into the solution phase, right? That is called chemical dissolution. What is electrochemical dissolution? It is a redox reaction, mostly redox reaction. Here what happens is, besides the chemical action, there will be also some electrochemical reaction, electron transfer also. For example, you take semiconducting minerals like uranium oxide. It is a semiconducting mineral. Once you put that particular thing in the presence of some oxygen or oxidizing conditions, and you have some reagent also, pH condition manipulation, this oxygen adsorbs on certain sites. When oxygen adsorbs on that certain sites, there will be transfer of electron from this particular surface, okay, labile surface, to the oxygen, transfer to the oxygen environment. So there will be happening, the charge gap will be happened there. Then there will be shift of the metal ion to that particular place. Once that happens, metallic ion is formed, ion is formed, that will be captured by the medium solvent which we are using for complexing. So that is how it happens. For example, you take uranium oxide. This uranium oxide dissociates into UO2 plus 2 and 2 electrons. These 2 electrons are captured by the adsorbed oxygen. So there will be generation of UO2 plus 2. This UO2 plus 2 travels across as this thin film, electrical double layer, and goes into the solution. Left alone, it complexes with the hydroxides present in the water molecules there and forms again insoluble uranyl hydroxide. In order to prevent that, you manipulate the pH conditions. That is, if you put it in the acidic medium, sulfate will be there, or chloride will be there, or nitrate will be there. So this UO2 plus 2 will complex with the nitrate ion or sulfate or chloride and forms corresponding thing which remains in solution for some time as long as the pH is maintained. Or in the alkaline conditions, you add sodium carbonate or sodium bicarbonate. That carbonate again complexes with UO2 plus 2 and keeps uranyl carbonate in solution. So here what is happening? There will be electron transfer from this particular thing, the adsorbed oxygen, and also there is complexation of UO2 plus 2 with the leachant which is present in the environment close to the double layer. So this is called electrochemical reaction mechanism. So what happens is, here the EMF of the system also plays a role, because this particular dissociation takes place only under certain conditions. Only under that ionization takes place, the release of electron takes place only under certain redox conditions. So the redox also plays a role besides the complexation ability of the leachant with the particular metal ion. Okay, that is why it has got depends on the electrical as well as this chemistry part. So that's why it is called electrochemical. It is not purely chemical like this or physical like this. It is electrochemical in nature. Now you see here, when you do leaching, what will happen? You take bastnasite. When you react with sulfuric acid, you got the rare earth sulfate formed. Similarly, when you take monazite, you got corresponding rare earth sulfate. That is how this dissolution takes place. This is again uranium. All these things. Okay. Now, besides the mineral of interest, there are so many other minerals present in the system. They also react. If you put sulfuric acid in any naturally pre-concentrate or ore, even mica reacts. Okay, iron reacts. Iron based minerals will react. Okay, like that. So what happens is, as a result of that, the solution is not pure. It is not selective. It is only taking maximum amount of the required mineral. Besides that, there will be dissolution of so many unwanted ions also. Like you see in the case of this one, this particular mineral, calcium will be there. Similarly, these are all types of mica. This one, potassium goes into solution. Here again, aluminum will be there. So all these things are present. That means the leach liquor which we are getting is not perfectly pure. Besides the element of our interest or metal ion of our interest, there are so many other cations, so many other anions present. We want to selectively take the metal ion of interest. So the second step is separation and purification. In leaching, you attain certain stage of purification. Okay, most of the quartz based minerals, most of the silicate based minerals, they remain intact, they are passive. But certain reactive, whatever we are designing or we are focusing on, those things come into solution in bulk. That is called leach recovery. You have to maximize the leach recovery of the wanted things. Okay, that will happen. Now in the second step, we do separation and purification. We try to again do a process wherein only the metal ion of interest can be taken out, the others are left behind. Okay, so what are the techniques used for this? That is called ion exchange based separation and solvent extraction based separation. In principle, both are same. One is using a solid phase for separation, that is ion exchange, which is insoluble in nature. Other one is liquid liquid extraction. See, both the separating liquid and the bulk phase remain liquids only. Okay, that is called liquid liquid separation. Here the separating thing is in the liquid form, the dissolved leachate will be in the liquid form, and the separating thing will be in the solid form in the ion exchange column. Again, when you come to the ion exchange column, this is a process of purification of aqueous solutions using solid polymeric ion exchange resin. Ions are exchanged between the two electrolytes. You have the leachate, okay, leach liquor, and you have this particular ion. These particular ion exchange resins are nothing but, you can see here. Yeah, you can see here. This is a polymeric thing. This is called resin. And on this resin, these are the functional parts. So actually the exchange takes place between the metal ion and the functional part. That is why it is called ion exchange. Ion exchange. Why it is called? Because the exchange takes place here. Before the adsorption of this particular ion of interest which is present in the leach liquor, there will be a counter ion. Once the solution is passed or leach liquor is passed, it displaces the earlier cation simply by two things. One is by mass action, other one is by selectivity. Which is having more chemical affinity, that will displace the earlier one. That is how the exchange takes place. So we have three types of exchangers: cation exchanger, anion exchanger, and amphotericity neutral exchanger. Three types of resins will be there. So depending upon the pH of the system, depending upon the characteristics of the dissolved metal ion, we choose either cation exchanger resin or anion exchange resin or neutral resin. These three things are chosen. Now, how do we do this? We actually have the leach liquor here, and in a column, this is packed with the resin. Once you pass the liquor through this, the exchange reactions takes place. This is called loading. And the solution which you are getting out is a barren solution, right? Once it is loaded, you have to elute it, because ultimately you have to recover it. So you have to elute it with a different solution called eluent. So during this process, two things takes place. One is separation or selective removal of the wanted from unwanted ions. Second thing is enrichment also. Because suppose this leach liquor contains something which is present at 1 gram per liter of, say, copper ion. You load it. Entire copper is loaded here. Say 30 grams of copper is loaded in 10 grams of resin or some 20 grams of resin. So it is called loading capacity. The loading capacity is always expressed as that many grams per liter of wet settled resin. That many liters of wet settled resin. Okay, it's many grams per wet settled resin. That is called loading capacity. Then you try to elute it. Whenever you are eluting, you don't have to use same volume of water. You can use reduced volume of eluent solution, so that by the time you pick it up here, you collect it here in the eluate, the concentration will be improving from 1 gram per liter to 10-15 gram per liter. That many times the enrichment of the metal ion in solution takes place by the process of this. So that is why loading capacity is significantly important. Higher the loading capacity, higher will be the enrichment ratio, and better will be the effectiveness of the resin. So before we actually choose a resin, we have to develop the loading curve. Not only the loading curve, we also have to develop the elution curve, because okay, it loaded, but I want 100% elution also. If it is not able to dissolve 100%, then what will happen? You are losing some material here. So the choice of the ion exchange resin should be in such a way that not good loading efficiency and equally good eluting efficiency. That is good adsorption and good desorption. So in order to have good loading, your resin is important. How you design the exchange parts of the resin. In order to have better elution, your choice of eluent is not only the type, including the concentration. That is, suppose you take sodium chloride. Sometimes if you use 0.1 molar sodium chloride, 50% only will be eluted. But if you use 2 molar sodium chloride, 100% will be eluted. Because the reason is the desorption is again based on law of mass action only. Desorption, as adsorption takes place by law of mass action, desorption also takes place by law of mass action. Okay, that is why the concentration and type of the eluent is also equally important to get a good this thing. Okay, so before we choose the entire system, we need to have both the loading curve and the elution curve. Based on that, we will be able to choose which type of ion exchange resin has to be taken for this. Normally, for lean liquor solutions, we use ion exchange, because compared to ion exchange and solvent extraction is very costlier. Therefore, you again in this liquid phase separation also, that is from the leachate separation purification, first you go to ion exchange, get some say level of enrichment, then you go for solvent extraction. That is all, that combination is always better. And of course, there is a rider here. Solvent extraction can work even in highly acidic environments, very high acidic environments, something point, see, for which you cannot measure the pH. Because if something is less than 1, pH 1, you will not say pH. pH 0.5 generally, that is not the terminology. You should tell only the acidity of the solution in terms of molarity. This many mole, this one normal, like that you have to tell. You should not say pH is 0, minus 0.1 or 0.5. That is not the terminology to be used. Under such conditions, highly acidic conditions, we have to go for solvent extraction only. And solvent extraction is the most widely used in the critical minerals, for the simple reason, again as I told beginning, that they are having high lattice energy, lot of acid concentration is required to dissolve them. Therefore, the acidity or the alkalinity will be very high. So the role of ion exchange in separation of these critical minerals is very limited, but solvent extraction, it will be more widely used, solvent extraction step. Now, when you come to the solvent extraction, how do we all know very well, that is a standard chemical engineering operation, wherein you have an aqueous phase and you have an organic phase. This organic phase is functionalized by the solvent. Okay, there is one called solvent, and in the solvent you put the active molecule and you have got the modifier. Okay, and when you do the equilibration, that is mix these things, there will be transfer of the required metal ion into the organic phase. Okay, this is called extraction. So whatever metal ion of interest is there, because of the selectivity of the solvent molecule in this, extracting molecule in this, it will be captured from the aqueous phase to the solvent phase, organic phase. Once it is taken, then again you drain off this aqueous thing. So you have exclusively the organic phase. You again equilibrate with some that is called extraction and scrubbing. In that scrubbing, what we do is, if there is any extraneous material that is coming into the organic phase, sometimes it happens, that will be removed. That is, those which are loosely held to the solvent molecule will be removed from the particular thing. That is called scrubbing. Scrubbing, or it is something called cleaning. That operation is there even in flotation also. Flotation, scrubbing, like that it is there. So essentially to remove the extraneous matter. Once it is scrubbing action is over, you put the organic phase along with again eluting phase. Okay, that is called stripping. First is loading, then is scrubbing, then is stripping. In the stripping part, what you do is you again take the aqueous phase loaded with some inorganic material, inorganic dissolved this thing, and then strip the metal ion which is present in the organic phase, which is held by the solvent molecule. You dissolve it, okay, and take it into the aqueous phase. So you got back the metal ion of interest into the aqueous phase in much purified form. So in this case also, we have to develop what is called Maccabe-Thies diagram. This Maccabe-Thies diagram will give you how many stages of the solvent extraction one need to do, because this is mostly equilibrium driven. Solvent extraction is equilibrium driven. So once the metal ion goes to here, there may be chance of that coming back into the aqueous phase. So you should you should see to it that entire thing comes into the organic phase. For that, you may have to have multiple steps. Okay, in solvent extraction circuit also, you will have counter currents extraction, you have co-current extraction, that type of systems. So they are all in detail if you go. Okay, so these type of things are there. Depending on your nature of extraction and all those things, you will have the choice for either counter current or co-current, that type of circuit decision. So after doing the solvent extraction, you will in general have highly purified solution. I will say the metal ion laden solution, which is suitable for precipitation or fit enough for precipitation of that particular thing. By doing this, you will get an intermediate grade product. It is not again highly pure, it is an intermediate grade product. So how do you precipitate? Again, precipitation in hydrometallurgy can take place by three things. Reagent addition, you add some other chemical reagent so that the solubility product, it exceeds the solubility product and precipitates the material. Or evaporation, once you evaporate, naturally the solubility product is this thing and then it settles, comes as a precipitate. Or by modifying the pH. Once you modify the pH, say pH 8, something is present in soluble form. Once you bring it to pH 11 or 12, it precipitates in the form of hydroxide. So pH manipulation also helps in precipitation of the dissolved material or metal ion. Okay, these are the three methods by which we precipitate the dissolved metal ion in the solution. Now, having done that, oh sorry. So those are the three basic steps which we use in solution purification or hydrometallurgy. Let us take one case study. I will just explain all these things by taking one case study. Except one. L12. So I am taking lithium because today we are all focusing our energies and all for getting cleaner environment. So energy storage is very important. I have taken lithium for that purpose because lithium based batteries are used quite extensively. That is the reason. Now what is lithium and why it is so valuable? Its atomic number is 3 in the periodic table of elements, very light, can store more energy per weight because weight is important for mobility of these vehicles and all, getting higher efficiency and all. Lithium is ideal for powering all these mobile, whatever you are using, mobile phones and all, smartphones, laptops, earbuds and all those things. You can see here specific energy density versus volumetric energy density. Lithium is having highest. Lighter weight, smaller size. We always require these things. Okay. As you see here, the demand for lithium is expected to increase by 132% by 2030 due to increased use of battery packs in the EV cells. 132% it is going to increase. You can imagine how much high will be the demand. Yes, people may say recycling, but to get the recycling equilibrium, some more time is required. No, we are still in the entry part. Recycling will happen after its end use is over. So still time is there for that. The compound annual growth rate of global lithium demand is 10%. You can imagine. Compounded annual growth rate is 10%. exorbitantly high. These are the lithium deposits in across the world. You have four types of deposits. One is brines, lithium bearing brines. Brines means salt solution only. Then lithium in pegmatite deposits. This is a geological formation. Lithium in sedimentary deposits and lithium in bauxite type deposits. For example, you take our Kashmir one, is bauxite type only. Okay. Whereas these brines are mostly present in ABC countries, Argentina, Bolivia, and Chile, right? And when you take pegmatites or sedimentary, they are called hard rock deposits. They are mostly present in Australia because Australia also is equally good competitor in lithium product resources as well as production also, right? India has got all the three types, but not in a very significant way. I will just give you this thing. Now, if you see the resources and production, from brines it is about 64% resources wise, and these hard rocks are 26%, sedimentary is 9%, unconventional resources, that is secondary resources like coal fly ash or some such thing, is about 1%. Production, if you take, this is how it distributes. Australia 46.92. Okay, total we have 1,30,000 tons in 2022, out of which 46 is from Australia, Chile is 30%, and then China is 14.62. Only production. I am not telling battery pack making. That again goes to China only. Okay, only the production, this thing. India does not produce lithium and depends mostly on import of the battery materials, mainly from China, Chile, Bolivia, Argentina, and Australia. We take from them. Total imports of lithium, lithium ion, lithium carbonates, and lithium oxide, different compounds of lithium, in the year from 2017 to 2023 is about US dollars 11.9 billions. Okay, this thing is sourced from a report, sourcing roadmap for India, lithium sourcing roadmap for India 2023 in International Institute for Sustainable Development, September 2023. These figures are taken from that. Okay, you can see the split in each sector. EVs, this is how it, you can see here, it is just 391 tons. But when you go to 2050 to 68,976, how high it is, you see. That itself shows the importance for lithium. Either you have in your own country or try to have mines abroad. Either of that. Okay. In India, if you see, we have primary resources in Karnataka. You can see there are three places. One is somewhere near Mysore, somewhere near Mangalore, again Raichur, that Amareshwar deposit. And Bihar, Jharkhand mica belt. There also it is available. In Jammu Kashmir, that is a recently found deposit, which I have told you is bauxite type. Secondary resources are present in Rajasthan. Lithium is present in the form of a mineral called ginevaldite in the tungsten deposits. It is present there. Then it is also present in coal fly ash. This is a recent discovery of eastern India. There is some concentration of lithium in the coal fly ash. Yes, we also have in brines in Rajasthan. Okay, how much is there? Please don't take any photographs. Okay, brines, right? So this thing. Now, something which is recorded, that is a different issue, but so how does it form in the brines? Let us see. Lithium in brine deposit primarily originates from weathering and leaching of lithium-rich rocks. Here, there are some lithium-rich rocks which undergo weathering and all those things. That is how it comes into a solution, gets concentrated. That is called salar. Salar means salt lakes, which contains dissolved lithium. This is how it is present in our Argentina, Bolivia, and Chile. Okay. Weathering and leaching of lithium-rich rocks, and those rocks are mostly rhyolites and shales into the groundwater. The lithium-rich water then flows into the enclosed basins. This is called basins, where evaporation and concentration process leads to the formation of lithium-rich brines. Because once it comes to a pond or a lake, evaporation takes place simultaneously. Therefore, the concentration also increases. Deep-seated hydrothermal fluids and water rock interactions can also contribute to the lithium. That is quite natural. Weathering action action that take place at high temperatures and pressures and hydrothermal fluids, all those things that happens. Now, how do we separate lithium from those brines? First of all, we have to see this. The salt-rich brines in the ABC triangle are pumped from beneath the crust, that's on the salar, and fed into a series of large shallow ponds. Artificial ponds are created. Initial 200 to 1000 ppm of lithium brine solutions is concentrated to 6000 ppm by virtue of evaporation. They are increased from as low as 200 to 6000 or from 1000 to 6000. This is the level of enrichment they get in those artificial ponds. Once they come here, mind it, it is not lithium alone. There are so many other ions also, because it is simple water removal. So many things which got dissolved from the rocks, they will be still present. You have to differentially precipitate them and get the lithium rich solution. How do we do that? That is how. From the brine, first you add lime, calcium hydroxide, which will be able to remove magnesium and other things. Okay. Then it is filtered, all those the precipitated material is taken out. Then it goes to sodium oxalate for calcium magnesium precipitation. There again it will be removed. Then it will be evaporated. Then subjected to purification by conventional methods. Ultimately you will get like a recarbonation and lithium carbonate is generated. This can be used for whatever purpose you want, convert into lithium hydroxide or some other lithium compound and use it in the product of your internet. That is the steps we follow from the brines. Quite simple, mostly these things. Now when you go to India, what do we have? We do have, but the concentration is very low, 25 to 35 ppm. Where is 1000 ppm, where is 200 ppm, where is 25, 30? At the same time, it is containing 40 to 50 grams per liter of sodium and magnesium. You can see the relative concentration of lithium vis-a-vis the other things. So how much will be the complexity of the process? As of now, we don't know. Tomorrow we may cite a better thing, but as of now. Today, recently, there is something called direct lithium extraction. Direct lithium extraction. Canadians and even in some places they are trying this. In direct lithium extraction from the salars, what they do is they just take it out, pump it to that surface and use appropriate extraction mechanism and remove it. There is no need for solar ponds, no need for all those things. They feel that these things that is bringing to surface and evaporating in the ponds, that is also environmentally harmful. So what they do is they increase the kinetics, they increase the efficiency by using the appropriate exchanger systems, solvent extraction or ion exchange, whatever it is, whichever is suitable, and then go for preparation of the material. So that is called direct lithium extraction, DLE technique. DLE technique. This has got the extraction portion, this portion, DLE where it is extracted, and then refining and injection. That is how. That means the water, the barren solution is put back into the thing. That is called injection. Okay, that is how they are maintaining the sustainability. That is the great thing. Whereas in the other case, it is just getting evaporated. Instead, you put it into that, into the raw, this thing, wherever it is there. That is the thing. Now, coming to the hard rock deposits, these are quite extensive in Australia. In India also it is there. What are the principal minerals of lithium? Spodumene, lepidolite and ginevaldite. These are the three things. The spodumene, the L12 content is 1.9 to 3.3. Theoretical is 3.73. And in lepidolite, it is 1.4 to 1.9. 3.56 is the theoretical one. In ginevaldite, it is 1.21 to 1.3. And theoretical is 1.7. This is what I am telling morning also. When I am telling you characterization, these are all naturally occurring materials. They may undergo so much of chemical reaction when they are present in the source itself. That is why the content differs from place to place, mineral to mineral laws. That is why they are giving range everywhere. Where is 1.9, where is 3.3, almost 70% above, right? And it is totally different from the theoretical one, right? That is the thing. That depends on the reactivity of the mineral. Now, in the hard rocks, The lithium is present either in the form of spodumene or in the form of lepidolite. These are the two principal minerals. How do we do that? In spodumene, first you comminuate it, followed by beneficiation, that is you pre-concentrate it. After you beneficiate, you do decryptation. What is decryptation? I will tell you. After you do decryptation, you go for this hydrometallurgical processing. In the case of lepidolite or ginevaldite, you do the beneficiation and directly go for roasting. In this case, you have a stage called decryptation. What is decryptation? Decryptation again goes back to this one. Yeah, sorry, this is. See, spodumene as such in nature is available in alpha form. So this is very, very refractory, chemically inactive. Okay. In order to make it chemically active, okay, it has to be loosened. Interatomic bonds should be loosened. So it will be converted from alpha to beta phase. Okay, this is more susceptible for leaching. So this is called decryptation. This will happen anywhere between 900 degrees centigrade to 1100 degrees centigrade. Okay, this is called decryptation process, that is loosening. Coming back again. The same thing is going like a toggle switch here. Ah, yes, we are here. So you understood what is decryptation. After it gets loosened from alpha to beta phase, you can go for pressure leaching or for roasting. That roasting again goes in two steps. I will explain you subsequently. Then once it goes for roasting and leaching, it will be separated by different method like ion exchange, solvent extraction and all. And ultimately by doing carbonation, you can get lithium carbonate. The next following slides will make you clear. So you take this lithium ores, beneficiation of lithium. Lithium ores often occur as hard rock complex aluminum silicate deposits known as pegmatites. What are the host of associated minerals in that? Along with lithium, you will have quartz, you will have plesioclase, you have potash feldspar, you have muscovite, spodumene, petalite, beryl, even in some places columbite tantalite is also available. All these things occur together. Therefore, if you want to separate spodumene from the rest, you have to design a beneficiation flow sheet. Some may be heavier than lithium, some may be lighter than lithium, some may be magnetic, some may not be magnetic. So you use a combination of these things for separating this. The lithium pegmatite ores contain lithium minerals such as spodumene, all those things, and then it also contains quartz, feldspar, and so on and so forth. Now, how do we do the beneficiation? This is the beneficiation flow sheet, generic one, which we follow for spodumene based materials. You have the ore, you crush it, then use the dense media separators. So in the dense media separators, DMS exploits the difference in the specific gravity between target and the gangue minerals. It is commonly used in the separation of spodumene. This is industrially used from other gangue silicate. For example, the specific gravity of spodumene is between 3.1 and 3.2. Say, this makes it slightly heavier than the gangue minerals like quartz, albite, and muscovite. Therefore, that particular thing is mixed with some material like ferrosilicon or something like that, appropriate one, depending upon the place. So the density will be able to distinguish, the density of the suspension medium will be able to distinguish spodumene from the other minerals. So spodumene is selectively taken into some fraction, quartz, albite and muscovite are separated out. After that, that is first stage of separation. Then comes your grinding further. After this grinding, you have another stage of dense media cyclones. Okay, here again further removal is there. That is followed by flotation. We use flotation. it is suggested that the 110 cleavage plane of spodumene is the most favorable site for oleate. As I was telling you in that molecular architecture thing, this is the most favorable site for adsorption of oleate on spodumene. And the chemisorption takes place. Flotation studies on wet and dry ground spodumene samples and found that wet ground spodumene has more of 110 and 100 crystal planes, while dry ground one has got 010. That is why we have to do always wet grinding, because only then you will have the adsorption of oleate on that particular thing. That is the most favorable cleavage plane. After you do that, you have the magnetic separation stage. In this, what we do, we remove the iron-based minerals. That is also present in the pegmatites. Those things are separated out and you get a concentrate which is exclusively rich in the spodumene. Okay, so you have done pre-concentration of spodumene by physical beneficiation. Now over. Now you have to extract lithium. How do we do that? Okay, this is actual thing. Just I will quickly run over. You have all these things. You do decryptation at 1100, then sulfation roasting using sulfuric acid, leach it, do the vacuum filtration, precipitation using lime in differential stages, remove iron, aluminum, etc., etc. Ultimately, you get lithium of 14% purity. Okay, right. After you get that, 14% pure lithium is only 80%. 14% grade lithium is only 80% pure, but you want 99 plus. So how do we do that? We take that particular thing, the material pre-concentrated lithium carbonate, by that first step of chemical processing, again redissolve it by putting in carbonated solution. During that process, what will happen? Only lithium dissolves, rest. Arre. Yes. Huh? No, no, in that you come down. I think it's easier to operate from here. There is some problem with this. No, jump. Next, next. Here. So when you do this series of carbonation, okay, then ion exchange or the filtration and evaporation and all those things, you will improve the lithium content from 14.95 to 18.69. 18.69 corresponds to almost 98%, 99% pure. So this is the method followed for this. Again, it consists of principally redissolution, evaporation or ion exchange. Ion exchange, that is by using an adsorbent and removing lithium selectively. Evaporation is the other way of increasing the concentration, and reprecipitation as lithium carbonate. This is how we take the lithium from that particular thing. Spodumene. Now, as a byproduct where it is present, if you take the tungsten ores of Rajasthan, along with the tungsten, there is a mineral called ginawaldite. It is mostly present in mica. So I have just circled this. It goes through crushing, grinding, and wet high intensity magnetic separation. Always remember that these micaceous minerals are weakly paramagnetic. So during the wet high intensity magnetic separation followed by flotation, they get enriched in the mica fraction. Mica, this is lithiferous mica. This ginawaldite is nothing but lithiferous mica. That is mica enriched in the lithium substituted. Okay, so it gets concentrated here. When it comes to this stage, again it goes through the same processing steps. That is salt roasting followed by leaching followed by all those things. That is the same way. But beneficiation is slightly different in this particular case. Now, very recently, it has come in the public domain only by our friends in CSIR labs that some of the coals in eastern part of India do contain lithium, and that lithium content is also very attractive. If you see here, you can see here the lithium in the coal of Australia is 8 to 34, China is 28 to 264, India is 26 to 353, not bad. Russia is 27 to 172, South Africa is like this. So this is in the coal. Generally, when you put this coal in a boiler, in a thermal plant, there will be enrichment of this so-called lithium 1.5 to 5 times. As it happens in rare earths, 10 times enrichment will be there from coal to coal fly ash. Okay, so if 50 ppm is present in the coal, it goes up to 500 ppm. 10 times is the general thumb rule. Here it goes 1.5 to 5 times and get enriched in the coal fly ash. But there is a catch here. Can we recover this coal lithium from the coal fly ash? Yes, it is. But there is a condition. What is that? They found that lithium recovery is better only when the fly ash is collected from those boilers which operate at temperatures less than 800-900 degrees centigrade. Here, if the temperature is more, lithium gets into the refractory form. That is that mullite and all those glassy phases. So leachability will be very difficult. So the boiler temperature is very important for seeing the feasibility of recovery of lithium from coal fly ash. But this is an area where people are working very, especially in countries like India where we don't have lithium, any large deposits, hard rock deposits, and so far no brines were recognized or identified. We should also look at the coal fly ash, map it, and see whether it can be recovered. Okay, this is an area of research actually. I will say like that. Now we tried to do on some coal fly ash. Okay, the what they say ballpark tests have shown that the lithium content in that particular feed is 37 ppm, very low. But once you do the leaching, it has just taken only 12 ppm. The residue is still containing 25 ppm. That means then we gone back to the thermal power plant that what is their temperature. They told 900 degrees centigrade. Then we understood what is the reason. So there are two reasons. One is the concentration itself is not very high. And second thing is the boiling temperature is also more. Therefore, because of these things, it is not effectively. But still, these are all areas where we need to do more and more research and come to some conclusion. Because mere presence of anything like rare earths or like this lithium and etc. in any fly ash, you cannot simply say by grade. You have to see the extractability. See, because they have got a standard procedure that is called a sequential chemical extraction. In the sequential chemical extraction, what they do is they increase the aggressiveness of the leachant and see where it is present, whether it is water soluble, whether it is bound to carbonates, whether it is present to iron oxides, or it is present to in a refractory surface, a refractory form in the glass. It got encapsulated in the glass. So this needs to be first diagnosed for each and every coal fly ash before coming or taking a judgment on how it can be extracted. No doubt, everywhere, even elsewhere in the world, people are even attempting to recover those which are present in glassy matrix also. No doubt. But ultimately, when it comes to the economics, what happens is you have to see how easy you can take it out. So if it is present in ion exchangeable form, that is the simplest of all. Today we are telling rare earths are more in China. It is not because that which is present in Bayana Obo. There is some other deposit where the heavy rare earths are present on other type of resources called ion adsorbed clays. Simply by passing some ammonium salt, they are able to dissolve all those heavy rare earths. And heavy rare earths value is very high. Lighter rare earths except for neodymium, nothing is very so. Whereas when you go to heavy rare earths, everything is important, like dysprosium is important, terbium is important. All these things are very important. So that is why people are eyeing on Myanmar also. Myanmar also has got that ion adsorbed clay type deposits. That is why that route is going. People are having interest on Myanmar. Understood? Unfortunately, in India, we have not yet cited any that type of ion adsorbed clay type deposits. People are exploring for that. That geological environment should be suitable for that. So, in essence, what I want to say is mere grade is not sufficient for taking a resource for exploitation. There are multiple things which we need to assess, diagnose, look into before selecting a particular thing, screening in a particular resource into a possible this thing, and it is more applied for critical minerals than anything else. Okay, all this we have to do that. There will be a lot of basic work which includes characterization, which includes diagnostic experiments, both physical as well as chemical, then making preliminary, that is called first order cost calculations. Only then we will be able to come to a conclusion whether we will be able to generate a material of whatever we are aiming at. So it is not critical mineral at any cost, it is critical mineral at some cost. Okay, this is what, with these words I think I can conclude my total lecture. Thank you for your patience. Also, not only coal, but the adjoining geological environments of coal. That is, there will be acid mine drainage in the coal fields. Okay, some liquid solutions also will be there. And as you said, that one, the other one, what is that you are making? Coal washeries also. We need to map it actually. We need to map and see. Only then we will be able to make any as such, because there is no generality anywhere. There is no general. Suppose they are in lignite, we cannot make a generalization every lignite contains. Similarly, bituminous, every bituminous contains. Not like that. So we need to have a case by case study and make a detailing. That's why mapping is very important. You take any country, they are doing extensive mapping. That is geometallurgy they are doing. Geometallurgy they are doing.
But if you look at the chemistry point of view, these grades, where do they prefer to stay with the coal mass? I mean, is there some
People say actually we did the microscopic, I mean that characterization also. In fact, US also they did. Mostly it is present in the form of monazite, or it is also present along with the organic matter. Organic matter. So when you boil it in the reactor, no, it will go into that liquid silica phases very quickly. Very rarely it is present in ion exchangeable form. Mostly it goes into that silicate phases only. That is the thing. Silicate phases mostly. So, but it is present as a discrete mineral also. If you see the deportment, again there are different things. There will be discrete monazite, discrete xenotime. There will be some ions present in the fly ash, encapsulated in the glassy matrix of the thing, silicate matrix. So like that it is there. You cannot pinpointedly say that it is present in the monazite form. But again, there is a limited success